Good morning, everyone. I'm Yoshi Kimoto, a data architect from DataStax. I'll be presenting today about what's new in Apache Cassandra 4.0. So 4.0 came out in July, and there's some enhancements and changes that have happened in it, and I'll be explaining about those, and notably about the new things that have been introduced. Okay, so we'll take a look back into a bit of a history for Apache Cassandra. So Cassandra was born like over a decade ago, and it graduated the Apache Foundation's incubation stage in 2010, and after that, the versions have been upgraded all along until this year's 4.0. In 2013, we had Cassandra 2.0 come out, and after a couple of years, in 2015, we have 3.0, and then after a couple of years, we have 3.11, which was the latest before 4.0 came out. Over these years, there had been a lot of enhancements there, where I put them on the screen so you can see. Like in 2.0, we had enhancement in CQL. We've implemented the lightweight transactions, role-based access control, user-defined types, and all that sort of thing. In 3.0, there was a massive rewrite of storage engine. We also introduced the time window compaction strategy, which was an enhancement over the date compaction strategy that was sort of oriented for the time series kind of data. And the hints were also implemented for file-based implementation. Before that, we implemented it as tables, but then those were sort of causing some challenges, so we've moved on to file-based hints, and that came in 3.x series. And we also had the materialized views come in. So there was a lot of enhancements there. And the last version of 2017 was when 3.11 was introduced. And 4.0 came after 4 years. So that was quite a long time. Actually, the new features were freezed in 2018. And the release of 4.0 after the feature freeze is 2021. So there was a long time after the feature was freezed until the actual release of Cassandra, which sort of suggests that there was a lot of testing going on, a lot of fixes introduced, and it came out in July this year. After that, the latest version right now is 4.0.1, which was released in September, like a month ago, right? So that's the latest state we are in. If you want to look at the if you're looking at updating, there's the instructions there in the news.txt file. If you download the Cassandra source, I mean the deployments, and also when you're thinking about upgrades, you would be able to upgrade from 3.0 and beyond. Those on the 2.x versions will not be a straight forward upgrade. I mean straight upgrade. You'd have to have steps going through 3, and then to 4. So as I said, there was a lot of enhancements and fixes. So there's more number of tickets, 61% more than the original 3 number of tickets that were submitted for 3. And also there was 140% more fixes built into Cassandra 4. So this sort of suggests that we have tested massively to make it stable. We have this pipeline of doing the tests for Cassandra, and we sort of invested there very much into making all the signals turn green for release, meaning that we don't see a test failure. So that was the main focus for it, and focusing to make it available so that you could put it into production from the get-go. Right. So that was the main goal. So after the release, the older versions, the 2.x versions, are not officially supported by the community right now. 3.0.25 is the latest release of the 3.0 series, and 3.11.11 is the latest for the 3.11 series. Those two are the ones that are the supported versions of the older versions, and 3.0 will be supported until 4.1 is released, which we sort of think is going to be around April next year. And that's the sort of cadence that we want to be in, sort of like release like point X series in a yearly cadence kind of thing. Okay. So that's the current state. So the main topic that we're going to talk about today is what's new. So there's a whole list of things. There's the whole slew of tickets that we've went through, but the things that I want to talk about today are one of the main, well, several of the main things that we've introduced. So one of them is virtual tables. Another of them is enhancement in the logging features. And then there's the streaming facility that has been enhanced as well. There's some functionality of back pressure, which is introduced a while back, and also in the other versions of Cassandra as well. And then there's some experimental features that are sort of interesting, and some other minor changes as well that I'll introduce in the end. Okay. So virtual tables. So what does that mean? Basically, it means this Java management extension kind of interfaces with the database. So traditionally, or the way that we interacted with the database in terms of metrics and all that kind of thing, and maybe controls, were through this JMX interface. And then we had sort of like a command line tool that would talk through the JMX, which is called NoTool. And we used to do that to look at the metrics, look at the status, do some tooling with the running instances and all that. And also looking at the settings as well. Looking at the settings was also was part of scanning the configuration files as well. So that was the way that we used to do it. But with the introduction of virtual tables, where you might find things similar in other databases, where you have like a table that you could query for the various informations that you need to look into the database for. Basically, at this point in time, the tables are read-only from the operation management perspective, and there's not that abundance of metrics and things that you could see, but we are working on it. The intention is to expand this, so you'll probably see more things coming in as we go. So another thing about is that we could select from a table, right? So there's like several types of tables that you can look into, like information about the cache, information about thread pools, information about the connecting clients, the tasks that are run on SS tables, also the configuration settings, and also virtual tables that provide information about the key spaces, the tables, and the column information. So you could select the virtual tables to look into those informations. For example, if you select from the the system virtual schema, key spaces, I mean the table in the system virtual schema key space, you could list all the tables in this database. thing is that the virtual tables are basically, it's not a cluster-wide kind of table. It's per node. So the information there is basically what you see as the node over there. So so that's that. So whichever node you're in and you connect to the SQL shell and do the select, you would see the information for that node. You could get information about client connectivities, who's accessing with what from where, kind of information. Then also you could look at like this configuration settings information, the current live configurations. Okay. So so these are the virtual tables. As I said, it's read-only. You can't update the configs using the virtual tables, but there is an intention to do that sort of thing if possible. So there's a list of things that you might want to look into from this URL if you're interested. So rather than interacting through JMX, interacting with virtual tables will be a bit simpler and easy to access. So the next thing we're going to talk about is the enhancement in the logging feature. So the logging has been enhanced quite a bit, where we could log information about what's happening in the database, as well as log information about the request itself. I mean, the queries itself. So there's these two logging features. One of them is the audit logging, and the other is the query logging. And then they have the interfaces for extending where to log the information. So currently, the implementation, as an implementation, we have writing it out into files, either in a text format or a binary format. So for audit login, basically, this is oriented towards compliance for workloads. So you want to understand who's accessing or who's doing what on which objects when, type of things. So these kind of features would be required when there's some compliance kind of policies in place. Of course. You specify what you want to log about, and there's various levels or categories of what you would want to log. And also, it will take information of who or which path those kind of access has come from. So basically, what it does is it will log the requests. I wrote queries, but basically it's the requests, and also about the authentication going on. The timing of log will be when, well, after executing an SQL statement or doing an authentication, and before sending the response. As I said, there's a pluggable logger layer where which provides an interface for implementing various types of ways to publish the audit events. So as I said, there's the binary log type, and there's the other feature that uses logback. So setting the audit, basically you would use the settings in Cassandra YAML file. You would either enable true or false, and there's various properties or attributes that you could set, like the key spaces that you want to look for, the categories, like whether it's the authentication or whether it's like DMLs or DDLs, those kind of things. So basically, you use the Cassandra YAML file to set those. You could also use the node tool to enable, disable on the fly, which basically means that it's a live config, meaning that it won't persist over a reboot. So if you need to do that, you need to do it with the Cassandra YAML file. To view the logs for the binary types, you would use the audit log viewer. And you specify the file for that. Okay. So the other logging feature we have is the full query logging feature. Basically, what it does is that it will log all of the CQL interactions. And you would capture that, and you could use that to reproduce what happened exactly. Right? So you would capture that, and you could replay those. So you could use the node tool to do that. Node tool enable full query log or disable it, or you could reset it using node tool. And then there's the FQL tool, the full query logging tool, to replay it or compare it with several versions of it or dump the contents of it. So you could use this feature for, of course, debugging, migration, and testing, or collect of what has happened on the node to understand what kind of queries or what kind of requests are coming in, maybe sort of behavioral understanding and kind of analysis may be done on those as well. Of course, you could use it to replay or reproduce some things that has happened. The nice thing about this is that, well, usually when you think about logging, it does, in certain cases, we find that it may impact performance because it sort of looks into the database path. But we're using the Chronicle queue of OpenHFT to alleviate that kind of load so that there's basically almost unnoticeable load even when doing these kinds of logs. So by the request logging feature, you could leverage them for the auditing facilities and of course doing the testings as well. Okay. Now, next is about faster streaming. So this is more about how you would stream data among the nodes. It's a feature which happens when you're bootstrapping, for example, and you would have to pass on data from one node to the other. The usual way, what happens is what we call stable streaming. So when a certain node has a request that he needs, or the node needs a certain range of tokens, or the partitions for a certain range of tokens, it will request it. The node that has that would prepare those ranges, read off from the table, prepare that packet, and push it over to the node that requested it, and then it's decomposed there. So it decompresses, it deserializes, it updates the states, and then serializes it again, and then pushes it into the disk as a stable file. So what happens is that there's if you think about the kernel, is like you have things going into the read it off from the user space into the kernel space, putting it onto the network, picks it up from the network, puts it back into the user space. And so there's a lot of same data copying within the kernel itself. So what we want to do is that sort of remove that kind of copying. So that's why we call it the zero copy streaming. So what happens is that, okay, give me this range of partitions when this request comes in. What we do is that, okay, so this SS table has that range. We're just going to send over that SS table, just copy it over. So that's it. We're just copying the file rather than serializing, deserializing, and doing all that kind of decompressing and all that kind of thing. So this brings down, brings up the speed, brings down the pressure on the pipeline between the nodes. It's enabled by default, but you could turn it off. The caveat is that it works for level compaction strategy, so that's something you have to have in mind. But the thing is that it will bring down bootstrap time drastically, and also it reduces GC pressure. So next up is client back pressure. So this is about introduction of the back pressure mechanism in Cassandra. So actually there's a blog post when you go to the Apache Cassandra website. You could read it in detail, but I'm going to talk about it right here for those interested. So the thing is that for each client that connects to a Cassandra node, well, basically you'll be connecting to the node, and that node would act as a coordinator, right? So for each client, they would have a netty channel that will connect to an event loop thread. And so the event loop thread will read off of the netty channel and push the request into an inbound queue, and which is then read off at the node to be processed. And once it's processed and the response is created, it is pushed back into the outbound event loop, which is then read back by the event loop that was that put in the request into the inbound queue. So for each event loop that is happening in the coordinator node, there's separate outbound queues, right? Think about the inbound queue is that it doesn't have a definite size, so it could grow indefinitely. Right? So the challenge was that when there's a lot of incoming requests, so there's a lot going on in the event loop and pushing it onto the inbound queue, and from the inbound queue, it's read off and then processed. But if the processing lags, the inbound queue would be growing, and the event queue, well, the event loop will keep on trying to push in the request. But while doing that, the outbound queue is being filled up with the responses. But because the event loop that is accepting the request and pushing it into the inbound queue is busy doing that, the request for the outbound, from the outbound queue to respond to the clients will be blocked, right? So there's a blockage happening there. And then because it's blocked, and the outbound queue is growing indefinitely, eventually you will be in an out of memory situation. So that was sort of a challenge that we have been having. So the solution was to provide a sort of a back pressure mechanism. So sort of we wanted to make a bound for the queues, right? So that's what we are going to set here using this configuration parameter. So by doing that, the queue will have a certain size, and if that size is reached, it will stop reading from the kernel socket inbound buffer, which will automatically, well, it sort of back pressures, the back pressure will be felt at the client side as well. So the client side will need to deal with that back pressure. So that's the mechanism to not break the node. So in this case, this is we're specifying the throw on overload parameter as false, meaning that basically it's just going to push back. When we set the throw on overload to true, what happens is that it will send back an exception. So in that sense, the client side would have to gracefully handle that exception. So depending on how you would want to handle that, there's two things that you would want to set. Well, there's two ways to set it: throw on overload, whether it's true or false. So basically, by doing that, so it's a sort of a throttling mechanism to keep the node healthy and keep the node being able to respond with a steady latency rather than increasing latency. So this provides you sort of a stable latency mechanism. Of course, you would need to handle the back pressure on the client side and think about how you would handle it. Okay. So this does help in slowing down sort of noisy clients or the ones that are bursting and keep the nodes healthy. If the clients are good enough and clients could scale sideways, for example, or you could have the nodes be scaled in a nice manner, then you could keep a certain peak rate in a controlled manner. Okay, so this is one of the mechanisms that was also introduced 4.0, but there's also the same in the older versions of Cassandra as well. So on to some of the experimental features. So talking about performance, there are various enhancements that were made to make the performance better for Cassandra, including, which we've already talked about, the zero copy streaming, but there's also enhancements in the Cassandra protocol itself, and also about various gossip level things as well. But one of the notable things that we're seeing, and we want to look into the future of even more better things, is the use of the new features in the new Java versions. So we've made it possible to compile Cassandra in Java 11. So currently you can compile it in Java 11 and run it in Java 11 environments, which means that you could use some of the features in Java 11. And also we are experimenting with Java 17 as well. So the Shenandoah and the ZGC functionalities, which is aiming to bring down the GC pressure or sort of virtually eliminate GCs, is something that we seeing quite some promise. So there's several tests that have been done where we are seeing promises, like how fast we could allocate, how much requests we could handle per second because of the lower GC pressures, getting better throughput, the average and P90 or 99 latencies are much better if you think of Shenandoah and also ZGC. So these are the graphs that were done using the beta versions of 4.0, where the tail latencies like the P99s and P999s are massively lower compared to the CMS versions of the same version of, even for the same version of Cassandra. Like we have the left side is key value workload, the right side is time series workload. And then there's another one for tabular workloads. Yeah, so there's a lot going on. Well, we see promises there, and we would love to hear more testing use cases, how things went, and that kind of thing. So yeah, we would love to hear people testing it on Shenandoah or ZGC. Another functionality that's also in the experimental mode is the transient replication. So this is also an interesting feature that was developed by Apple. So it sort of provides you with a way to have a temporary replica, which is replicated to the actual replica using incremental repairs. So how this works is what I'm going to explain now. So in the normal way of thinking is that when you have a replication factor of 3, the write request will go to the 3 destination nodes. And when you read with a consistency level of quorum, basically what is expected is that you would be able to read what you have written. So providing with the confidence of the consistency. So in the case of transient replica, you would specify a replica other than the main replicas that you're going to have. So if you have a replication factor of 3, you could specify that, okay, there's going to be 3 nodes that will be receiving the replicas, but we're also going to designate a separate node to be a transient holder of another replica. By doing that, what happens is that if the actual destination replica is down, rather than holding a pile of hints, to write to the transient replica, and you could read from the transient replica as well, as long as it holds there. It holds the replica there. And during the incremental repair, the transient replica will be, if the actual destination node is back up, the transient replica will be replicated to the original replica and then removed after that. So this provides you sort of a way in helping when nodes are down or reducing the load on about the hints and all that. So the way you would specify is, you specify sort of like a portion-ish kind of specification. So 3/11 means that you're going to have the 3 replicas, but 1 transient replica as well. Okay, other enhancements and changes. There's a whole list of it, but some of the notable ones. I've already talked about this. We have support for Java 11, still experimental, but there's a blog on the Cassandra Apache org site where, well, it's not an org, but it's a documentation that explains how you would want to compile in Java 11. And if compiling in Java 11 means that you would run it in Java 11. It will not run in Java 8. Of course, and there's other enhancements as well. As I said, for performance enhancements, the messaging and streaming, the async features have been introduced. Also, there has been removal of deprecated features like the thrift feature and also the compact storage feature that's aligned with it. We also have a feature that would restrict accesses on a role, for a role, to a certain data center. So if you want to restrict a certain role to access only a certain data center, you could do that. There's also a bit of an enhancement in CDC, change data capture feature. And also changes in the read repair. So there's been sort of like a advice that you wouldn't want to really use the read repair chances. So that has been removed. And also, we've also have a feature that would be able to turn off blocking read repairs as well. We also added some functionality in the node tool repair feature, which provides you with the preview and the validate. So preview and validate are similar things, but basically what it does is that it will do a simulation of a repair, meaning that it will create a Merkle tree and compare it and see how much work is going to happen, what is going to happen, or actually compare the validate is more about comparing the Merkle trees and see whether the repair has actually repaired things. So that's something. And SS stable dump has been enhanced so that you could grab JSON output of on a per partition based dump. And also we've added a network topology strategy, replication factor expansion feature that would automatically be expanded to all the available DCs. Some of the features in the SQL language itself have been added, like support for functions like current timestamp, current date, current time UUID have been added. Also, there's arithmetic operations that could be done in the statements, like -2 hours or +2 days kind of arithmetic things. Also, adding the use of simple operators within a SQL statement, like all the operator signs. We also have a support for Python 3 or SQL shell. So now we support both Python 2.7 and 3.6. Okay. And actually, there's a lot more deep dive in the new features. We have this site in DataStax where you could actually read more deeper into it. If you look at the bottom right of the slide, it says approximately 3 hours. So what I've done is condense this into like 45-minute talk, but if you want to go deeper, there's 3 hours worth of reading and actually hands-on parts of it as well. So if you're interested in learning more about the actualities of what's been introduced in 4.0, and maybe also about thinking about how am I going to upgrade my Cassandra clusters. So those informations can be found in these learning series that we have created. Okay. So 4.0 was a lot about enhancements and fixes so that you could run it in production from 4.0. In the past, people used to say that maybe we could wait for like several patch versions until we actually put it into production, but we know now that people are running it 4.0 in production. So say it's good for production. So we'd be happy if you would download and start using it. The other things beyond 4.0, because 4.0 is out now, we are looking into more new things. So there's a lot of things being discussed in the Cassandra community. And one of the things as a process we've evolved in the past 3-4 years is the enhancement proposal and procedure. So currently there's a procedure where there's a way you would be able to submit a proposal and feature enhancements, and well, you sort of document what you are going to propose, like this is the objective, this is what you have to do, this is the things that we have considered, and this is the path we want to do. So there's a lot of that going on, and currently the latest list we have is this one. While 4.0 was still in testing phases, we didn't have adopted ones yet, but now over several votings, there are several CPs that have been accepted. And probably interesting ones will be the Paxos improvements as well as the general purpose transactions, which have had a whole lot of discussion on the Cassandra dev mailing list. And it is a very, 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 very interesting reading if you go through the emails exchanged, and also if you look into the proposal, and also there's accompanying paper for it. And it is very interesting. So we are looking forward to what this brings in the future. And yeah, so the adopted ones are there. Others that are under discussion. So there's a session in the afternoon about having Apache run on the Kubernetes environment. So there's CP that are aimed towards those use cases, like about the Kubernetes operator. There's also the I think there was the sidecar one as well, and others that will be coming. Also, there's another one called the storage attack index, which is another implementation of a secondary index, which is having, rather than having a secondary index as a sort of a lookup table, having an index file accompanying the SS table file. So, which does bring a lot of less pressure on GC and better storage use, I think. And there's a lot of others in draft still, and in the dev mailing list, there's some people looking to submit other CPs. So we are looking forward to that. and looking to even more new interesting features that will make things even better. Yeah. So calling out to the community, we hope you will download Cassandra 4.0 or 4.0.1 now, and try it out. Okay, so that is all from me.
Hi everyone, my name is Paul Brebner. I'm the technology evangelist at Instacluster. I'm giving this presentation from my office in Canberra at home. So thanks for the invite to talk today. I hope the talk fits in with the rest of the content. That was a great introduction to Cassandra 4.0 I just listened to. Thanks to Yoshi for that. That was very interesting. So mine's a slightly different talk. I'm talking about massively scalable real-time geospatial data processing, primarily with Apache Cassandra as the focus. So I mentioned I'm the technology evangelist at Instacluster. That sort of means that I get to play with lots of interesting new open source technologies. I build new example applications using them while I'm learning. I blog about them. And occasionally I get to give a talk, so it's good to actually be presenting to a live audience. In this case, I've done a lot of virtual conferences in the last 2 years, and this one's actually live, which is far more exciting. So yeah, there's a whole lot of technologies I've talked about. Most of them are Apache ones. There are some other open source technologies like Prometheus, the Bayesian, Open Search, Redis, and things as well, and they're all available on instacluster.com/Paul Brebner. I think I'm up to about 73 blogs there. So I've been doing that for 4 years. It's a bit of an ongoing process. There's always more to learn. Just a bit about Instacluster. We have a managed platform for open source technologies. It's a complete ecosystem to support mission-critical open source big data applications for multiple use cases, everything from gaming through to sort of IoT. For storage, we have Cassandra, Redis, and PostgreSQL, which is only a recent addition. Streaming, we have Kafka and Kafka Connect. For analysis, we have Apache Spark. And for search, we support OpenSearch and Kibana. And we provide that as a managed service. We do consulting and lots of education around these technologies as well. And I guess one of the features is it's multi-cloud. So we support this on lots of different cloud platforms all around the world. So this talk is focusing specifically on Apache Cassandra with some help from Apache Kafka as well. So here's a bit of an overview. In the last few years, we're going to have a look at location in the news. The particular use case I'm focusing on is anomaly detection, and we'll have a look at how the application was built and some baseline throughput data we got for that. We'll have a look at the spatial anomaly detection problem, which is a bit of a variant on the original one. This was sort of an extension I did over a course of a month last year. And have a look then at some solutions, primarily focusing around how Cassandra solves some of those problems, how you represent location, and then how you query and index location data in Cassandra. And surprisingly, there's actually quite a lot of different options, which is why I had to have a bit of a journey through those and test some of them out and see which ones actually work best. So there's things like bounding boxes, secondary indexes, geohashes, Lucene index, and then we'll compare some performance results and then extend it again for 3D as well. In the news in the last few years, you may have heard of John Conway. He was a bit of a legendary computer scientist. He passed away last year, I think it was. He's quite famous for a number of things, but the one I remember him for is the game of life, which is a cellular automata. The next state of each cell depends only on the state of the immediate neighbors. So that's got a very specific location aspect to it. It's got very simple rules, but you can end up with some amazingly complex patterns. That's a particularly astonishing one that I found. Also in the news, unfortunately, in the last couple of years, we've all been social distancing and been trying to have COVID-19 tracing that actually works. Here is something that I discovered on a New Zealand YouTube channel, Uncle Ron's Social Distancing 3000 invention. I actually think that was probably a very sensible approach for social distancing, given that the some of the apps that they tried, including the Australian government COVID Safe app really didn't do what they were advertised for, unfortunately. Also in the news, we had a bit of a near miss, haven't we? There was an asteroid that missed the Earth in April last year, and it actually came inside the moon's orbit, I think. So that was a bit of a near miss. So previously I presented a talk at Apache Con a couple of years ago now, both in the US and in Berlin, on the main application that we built. This was Kafka, Cassandra, and Kubernetes at scale, real-time anomaly detection on 19 billion events a day. So it was a pretty big number. We sort of made it into a bit of a news story. 19 billion anomaly checks a day using a whole bunch of open source technologies. So the problem of anomaly detection itself, basically it's how do you spot the difference in the stream of events at speed, say definitely less than one second, and at scale. So you've got both high throughput and also a vast amount of data as well. How does it work? Well, I picked a very simple way of doing the anomaly detection processing. It's called cumulative sum control chart. It actually originated from the 60s. It's a method which uses statistical analysis of historical data. Data is a single variable or key at a time, but you can potentially have billions of keys. So this is one of the dimensions of the large data size to it. So you can't have everything in memory. You have to be able to store the historical events on disk. And there's a window, a period of time, or a number of events that you look back over to see whether there's been a significant change detected. So we picked a relatively simple algorithm for this because we wanted the focus of the exercise to be on the data layers. We wanted to put the most stress on the data layers themselves rather than CPU and processing overhead. So we built a pipeline. It's got Kafka, Cassandra, and Kubernetes clusters. Kafka handles the streaming, and Cassandra handles the data storage, and Kubernetes was used for the application scaling itself. Cassandra provided efficient data writes and reads with the key, which is something like a unique count ID or a sensor ID or something like that. So that's a bit of an overview of the application, the three main clusters, and the sort of the pipeline. Basically, an event comes in, we store the event into Cassandra, we then get the historic data for that, the key associated with the event, run the fraud or the anomaly detector or fraud detector it could be in a financial context, and then decide whether it's likely to be an anomaly or not. So looking a bit more in detail at the Cassandra data model, basically events are a time series. The ID is a partition key, and time is the clustering key, which has an order over it. And the read gets the most 50 values for the ID, and it's very fast. So here's an example of creating a table with that data in it, and then doing a select for a particular ID and getting the first 50 results back, ordered by time. So we ran that application and that query on quite a large cluster to get some impressive results. We didn't really have an upper bound that we had in mind, but we just sort of kept on going until we thought, oh, that's a pretty big number. We like the look of that. So we used 574 CPU cores in total across the three clusters. You will notice that the Cassandra cluster was the most demanding part of the system that had 384 cores, followed by the actual application pipeline, and then probably the least demanding part of the system was Kafka itself. So the baseline throughput was 19 billion anomaly checks a day. So for this, we focus on the geospatial anomaly detection in this talk. I'll actually just normalize that to what I would call 100%. So from now on, I'll refer to that as sort of the 100% figure, and we will compare some of the results we get against that normalized value. So we'll introduce now the harder problem, which is to spot the differences in space as well as time. So space is big. This is a famous quote from the Hitchhiker's Guide to the Galaxy. Yeah, it's big basically. It's got like scale, and yeah, there can be things happening locally or further away or essentially at an infinite distance. But yeah, it's big. So it's interesting when geospatial data processing actually was the traditional big data problem in a sense, which drove a lot of the developments in technologies over the years, and it's still a relevant problem as well. And you can have spatial anomalies, for example, in the Star Trek universe. You can imagine the the enterprise coming across lots of different weird spatial anomalies. Someone's actually classified these in a list. How about a real example though? Well, Jon Snow, well, not this one, slightly old series now, but anyway, going back even older though, here is Jon Snow's 1854 cholera map of London. They had an outbreak of cholera, and they wanted to know what was causing it. And what they did was they actually mapped the deaths per household and location, and they actually were able to use that to identify a single polluted water pump that was causing the outbreak. And there were some outliers. For example, it turned out that there was a brewery right next to the pump, but none of the brewers got sick. And why is that? Well, brewers drink beer, not water. So yes, your anomaly detection system has to be able to cope with a few outliers as well. Okay, so to be able to do geospatial anomaly detection, first you have to know where you are. So you have to have some representation of location that includes a coordinate system, a map, and a scale. And unfortunately, this poor guy in the desert here has come across a map that has none of those things, so that's entirely useless. This is a slightly better map, a Treasure Island map. It has location in terms of lat-long coordinates. It's got a scale, if you look down the bottom, English miles, whatever they are, and it's got interesting locations with annotations, like the bulk of the treasure is here. It looks pretty cool. So geospatial anomaly detection was a new problem for me and for my application. So rather than having just a single ID, the events now have the location, as well as some sort of value associated with that location. So the problem now is to find the nearest 50 events to each new event, and we still want to do it quickly and under 1 second and at high throughput as well. Unfortunately, we can't make any assumptions about geospatial properties of events, including things like location, density, or distribution, i.e. where or how many are in a particular area. So that means we need to search from the smallest to increasingly larger areas. Some anomalies, geospatial anomalies, such as this one here on this picture, is actually pretty big. So we can't make any assumptions about the size, initially at least. There was a very interesting talk at ApacheCon in 2019 where the guys from Uber were talking about a similar problem and using similar technologies, in fact, to be able to forecast demand in particular locations in cities. And they had to increase the area size until they had sufficient data to make more accurate predictions. So the first thing I thought was, well, can we just use the latitude, longitude coordinates as the Cassandra partition key? Well, yes, in theory, compound partition keys are allowed in Cassandra, but you can only select the exact locations, which is not very useful for our application. So how to compute nearness? Well, in general, to compute distance between locations, you also need a coordinate system. For example, this is the Mercator map. It's got a few problems, unfortunately. It assumes a flat Earth, and there is quite bad distortion near the poles. For example, if you look at that, the southern continent of Antarctica looks enormous, and it's actually not that big. In reality, the world is approximately, at least, spherical. So there is a complex mathematical calculation which gives you the distance between 2 points. So it's non-trivial to do that calculation, unfortunately. So there are some approximation methods. A bounding box is a well-known one. It's an approximation of distance using inequalities. Basically, if you know the location of each of the corners of the box and a location that you want to check, you can check to see whether that is inside the box using some inequalities, as in the example here. So that's computationally simpler. It doesn't have any nasty mathematical functions or anything, and accurate enough for some use cases. So how would you do bounding boxes and Cassandra? Well, using something like a country partition key and lat long and time as the clustering keys, you can create a table with that data and then try and run a query such as this one here. Unfortunately, you get an error. So basically, you can't run queries with multiple inequalities like this, unfortunately. Okay, so another approach is to use secondary indexes. How well do these work? Well, there are the standard built-in Cassandra secondary indexes. So you could create an index on the latitude and an index on the longitude, but it turns out you have the same restrictions as the clustering columns. You can't have multiple inequalities in the query. SASEs are another option as well. That stands for SS Table Attached Secondary Indexes, a bit of a mouthful. This supports more complex queries more efficiently. So similar to the above example, if you create two SASE indexes on lat and long respectively and run a query on it, that does actually work. You don't get an error. However, if you read the documentation, it says allow filtering may be inefficient. So if you've got multiple rows being retrieved, you actually have to retrieve the rows, then do the filtering, and typically isn't suitable for production. So that seems like a bit of a dead end, although I must admit, having looked at the SASE documents themselves in a bit more detail, it says even though allow filtering must be used with two or more column inequalities, there is actually no filtering taking place. So I'm not so convinced that that would be a problem or not, although the performance results may tell the complete story, which are here. So here's the first lot of results. So remember I mentioned that 100% is the original 19 billion checks a day. Unfortunately, using the SASE index, we get very, very poor results in comparison, well under 1% of these. So that doesn't seem like an option if you are concerned at all about maintaining the scalability and throughput of the results. So another approach, geohashes to the rescue. You can divide maps into named and hierarchical areas. We've also sort of used something already using a country partition key. There are other domains where this is quite well known and very common. For example, plate tectonics, they're actually hierarchical, which I hadn't realized. There's the big plates, and then there's actually subplates, which form a hierarchy under each of the major plates as well. So hierarchical data and geohashes sort of go together. Just a bit of background about geohashes. There are different approaches and standards for geohashes. This is just an example that I used. Basically, a geohash is a rectangular area. It's a variable length base 32 string. A single character region is something like 5,000 by 5,000 kilometers in size. And each extra letter you add gives 32 sub areas. And if you have an 8-character geohash, that gives you about a 40 meter by 20 meter rectangle anywhere on the planet. You have to encode and then decode lat long to and from the geohashes, so there's a bit of extra effort there. And unfortunately, there are some edge cases, and it becomes increasingly non-linear near the poles, so it's not perfect. It's an approximate technique. So oddly enough, some geohashes are real words. Ketchup is in Africa. It's 153 meters by 153 meters for ketchup. And Trump is in Kazakhstan. He's got an area about 5K by 5K. So we modified the anomaly detector application to use geohashes. Lat long is encoded as geohash. Geohash now becomes the new key that we use, and then the geohash is used to query Cassandra. Again, there's a couple of different options for implementing geohashes in Cassandra. Option one, and some of these are a bit silly, to be honest. I was also learning Cassandra and some of the subtleties of Cassandra indexing at the time. So I don't think someone who is more expert in Cassandra may not have even tried some of these options, but I'll present them anyway just to show some of the things that I considered. Option one is multiple indexed geohash columns. So in theory, geohashes work really well for database indexes. That's one of the sort of the good fits that they have. So here's an example that I tried with 8 geohash columns, and yeah, you had to create 8 indexes as well. Then you have to run a query essentially starting from the smallest to the largest areas, and then you stop when you've got 50 rows of data being returned. There's some trade-offs with this approach: multiple secondary columns and indexes for a start, multiple queries that you need to run. Accuracy and number of queries depends on the spatial distribution and the density, which, yeah, that'll always be the case. Results, well, slightly better, so a bit more optimistic this time. So this gives us about 10% of the baseline throughput, which is about 1.9 billion checks a day. So it's certainly not as bad as the previous approaches we tried. Option 2 for geohashes is using denormalized multiple tables. Well, so it turns out that in Cassandra, denormalization is pretty normal. So that's something, a bit of a mind shift that you have to adapt to in a lot of the NoSQL databases, and Cassandra in particular. So it's perfectly acceptable to denormalize your data into multiple tables. So that's what I did. I created 8 tables, one for each geohash length, as in the example there, missing the ones in between. And then you select again from the smallest to the largest area using the corresponding table. Again, there's some trade-offs. You have to have multiple tables and writes, more importantly, and also multiple queries as well. Did it work better? It did. So this option actually gave us 20% of the baseline throughput. So it is certainly a better choice in terms of throughput at this point. Option 3 is to use clustering columns. This is similar to option 1, but using clustering columns instead of the option 1. So there's an example of the 8 clustering columns. Yep. How do they work? Well, so how do clustering columns work in general? Well, they're very good for hierarchical data modeling. So they're good for the modeling, and they're also good for the efficient querying of hierarchical or nested data. There's a few constraints around clustering columns. In particular, the query must include higher level columns with the equality operator only. Ranges are allowed on the last column in the query, and lower level columns don't have to be included. So here's an example of query over clustering columns. We've got a couple of equalities there, and then a couple of inequalities, and we haven't included all of the columns. So that does work. But in terms of having multiple clustering columns, well, actually one is enough. So here's potentially a better solution: a single geohash clustering column. So you just use a geohash 8 and time as the clustering keys. So it's quite a lot simpler. And there's your inequality range query. Again, you just have multiple queries potentially and stop when you get 50 results back. And this gives better results again. So we'll call this one option 3. It's better. It gives 34% of the original baseline, which is about 6.5 billion anomaly checks a day. So that's certainly an improvement over all the other alternatives that we've looked at so far. So yeah, with spatial data, there's potentially some compounding issues. You've got to think about things like the cardinality for the partition key should be quite big potentially, which corresponds to about 4 or more characters in the geohash. So it's not going to work too well for the shorter geohashes. In general, unbounded partitions are bad, so you may need composite partition keys in production. You may need to create a bucket out of something, including time, for example. Space versus time is a tricky trade-off. You could have different sized buckets for different size spaces. So bigger areas with more frequent events may need shorter time buckets to limit the size. And this may well depend on the space-time scales or the underlying systems and process that you're trying to model. So, for example, I've got a picture there of spatial and temporal scales for oceanographic processes, and some of them are actually very small, some are massive as well, and some are sort of skewed in terms of they're big spatially, but maybe not very big temporally as well. So yeah, it depends on what you're trying to model as to whether it's going to work and how well it's going to work. It's tricky. So another option that we had to look at is the Cassandra Apache Leucine Index plugin, which is basically a concordance. If anyone remembers the days of physical book concordances, they were often bigger than the book that they were indexing. Typically a concordance for the Bible, for example, was a lot bigger than the actual copy of the Bible itself. The Cassandra Leucine Index plugin, it's a plugin for Apache Cassandra. It extends its index functionality to provide near real-time search, including things like full-time search capabilities and free multivariable, geospatial, and bitemporal search. It's achieved through an Apache Leucine-based implementation of the Cassandra secondary index, where each node of the cluster indexes its own data. Luckily, Instacluster actually supports this plugin, so I knew about it and it was available on our managed service, so I didn't have to go to any trouble to try it out. It's an additional add-on to our managed Cassandra service. You just click the extra box that says, "Can I have this, please?" And we support the code, so you can actually look at the open source code on our GitHub there as well. So how does this help for geospatial queries? Well, it's got very rich geospatial semantics, including things like geopoints, geoshapes, geodistance search, geo-bounding box search, geoshape search, multiple distance units, geotransformations, and complex geoshapes, most of which I didn't need. So here's an example, a geopoint example for a start. Under the hood, the indexing is done actually using a tree structure with geohashes with configurable precision. So we are actually basically using geohashes, even though we didn't realize it. So here's an example of creating the table, and then we create the custom index, which has a lot of sort of configuration stuff in there, which is Leucine specific at that point. And there's multiple search options, as it turns out. So there's different ways of being able to retrieve the data. You can try and sort it. Sort has very sophisticated but complex semantics. You have to read the documents for that, basically. Another option, it does implement the bounding box filter. You need to compute the box corners in the query. It also has support for geodistance filtering, as in that example there. Prefix filter as well. Prefix search is quite useful for searching larger areas over a single geohash column. And you can basically search for a substring, which corresponds to a smaller area of the full-length geohash. And that's actually very similar to the inequality over the clustering column approach that we've already tried. So some Leucine results. We tried a few of those. We tried sort, the bounded box, geodistance, and the prefix over a geohash. The best one was the prefix filter over the geohash that gave us 25% of the baseline throughput, which is about 4.7 billion checks a day, which isn't too bad either. So looking at the results overall now, all of the geohash options are certainly faster. The best one gave us the 6.5 billion anomaly checks a day. The Leucine bounded box geodistance was probably the most accurate. So there's a trade-off here between performance and accuracy typically, but they only gave 5% of the baseline performance. So that's quite a drop in throughput if you choose to use those. And I thought we'd add an extra complication at this point. Let's go up and down potentially. So 3D, up till now we've been thinking about space as purely two-dimensional. There's no up and down in a 2D world, in a flat world. But I don't know, people last century, or maybe it's a century before now, some of them didn't actually believe that the world was round anyway, and they managed to explain away the geography of their local area, at least in terms of a square and stationary model of the Earth. Very strange. But if you do want 3D, then you need location, altitude, and volume. So there are things called 3D geohashes. They represent 2D location plus altitude and volume. So for example, here is a 3D geohash, which is a cube with all the Earth's water in it. So there isn't as much water as I thought. How would you apply 3D geospatial anomaly detection? Well, potentially a current sort of a trend is drone delivery. So maybe you could use a system like this for 3D drone proximity detection, so you could avoid crashes or avoid breaking any rules around where you're allowed to fly drones and things like that. So it turns out there are actually a whole bunch of rules around using drones. For example, you're not allowed to use them within 50 meters of people and property, 150 meters from congested areas, 1 kilometer from airports, and 5 kilometers from exclusion zones. And interestingly enough, these distances actually correspond almost perfectly to specific length of 3D geohashes. So you can basically just plug in a 3D geohash and it should work. Unfortunately, I was hoping that we could get drone deliveries at my house. We're actually in the region for one of Google's startup things where they're doing they're trialing drone deliveries of small objects up to about 1.5 kilos. But when I typed in my address and everything, they said, sorry, we can't deliver to you. Possibly, unfortunately, all of the rules associated with the drone delivery are violated for my house, maybe, I don't know. So some results with 3D geohashes. So as I mentioned, 3D geohashes basically work with all the geohash index options that we've already looked at. It's pretty fast. There's no difference in speed to perform the 3D proximity checks. And look, in general, if you do need more throughput, of course, for a Cassandra cluster, you just use a bigger, more powerful Cassandra cluster. That's one of the advantages of Cassandra. Yep. So I actually built some 3D demo geohash Java code. It's available on my GitHub. There's the URL there. It produces valid 3D geohashes for altitudes from 13 kilometers below sea level to roughly geostationary satellite orbit. So just about the entire range of things that you might be interested in from an Earth perspective. And it can be used for any of the geohash options that I've already mentioned. So if you want some more information about this topic in particular, or any of the other open source technologies that I've blogged around, including quite a lot of different use cases, such as IoT, machine learning over machine data. I've done a series recently on using Cassandra for a globally distributed low latency financial application in multiple locations. So yeah, I try and come up with interesting use cases and then find the most relevant technologies and talk about how they can be used. So they're all there at that link there. And finally, if you want to try out any of these open source technologies, we've got a free trial offer on our main website. And one of our newest offerings is in public preview at the moment, which is managed PostgreSQL, which I've only just recently learned and started playing with, and it's pretty cool. It doesn't have the horizontal scalability of Cassandra, but it's actually quite a cool technology. It's been around for a long time, and it's great for JSON data, for example. So I've been using it to build JSON pipelines and things, so that's quite fun. So that's the end of the talk. Thanks very much for your attention. I hope that was relevant and interesting and useful. Yep, and it was fun giving a live presentation again. So thank you very much, everyone, and I'll hand back over to the main organizer now. Bye.
someone new now. I have more room, no more formats to chain me. On the same page, we are effortless, schemaless, living in the future, you and me, made for us, serverless.
Okay, hello. So let's start with the. I'm going to cover the Cassandra. What you can say that on Kubernetes. Now every day, everyone is moving toward the Kubernetes, and I will show you how quickly and faster you can do your deployments of the Cassandra on the Kubernetes. Okay, so first of all, I'd like to welcome all of you on this Cassandra day, and I will take you through some basic concepts of Cassandra. Then I will introduce our operator to you, which will make it very easy for all of us you to deploy the Cassandra on Kubernetes. Then how we can monitor our cluster which is running on the Kubernetes. Then we will work with some data. We will try to see how we can access the cluster actually, and how we are going to get into the cluster which is running in the Kubernetes because from our local machines. And then some of the steps for scaling up and down, what is a Stargate API, little bit on that, because after me there will be a complete session on Stargate, and then how the repairs are running as a different service, and then quick wrap up on this particular what I can say that Kubernetes, Cassandra on Kubernetes. Okay, so now let's see what was the infrastructure earlier. Whenever we are deploying anything, if you need to deploy something, you have to first set up an infrastructure, and then you will have the data layer, data getting stored on your infrastructure, on your databases running on an infrastructure, and then you have the applications to connect to that database. And it is a very tedious job. Now everyone is moving from the what I can say that from the monolithic to the microservices, because it will make ease of using the services also simpler and fast also. And now everybody is talking about the Kubernetes, microservices, and all that kind of stuff. Now we are seeing the shift also on the database. Earlier, the people were worried about running the databases on the containers or Dockers due to the persistence and other things. Now you will see everybody slowly moving toward the Kubernetes for databases also. Most of the databases now can be ran as the what I can say that a container on top of a Kubernetes, because Kubernetes give a lot of flexibility to the database. Okay. The one thing is that you can have any infrastructure. It's an in-house private cloud. You're running it on a VMware. You have a physical server. Anywhere you can set up your infrastructure and you can start using it. And you can easily do lift and shift because it's an hardware dependent. You can run your pod on the Kubernetes. You can on GCP. You can run your same pod on your system, same machine, on your local machine also. And then we have the Kubernetes as an orchestration engine. So what's an orchestration? Orchestration is if we see a simple meaning of an orchestration, it is something which help us to run something smoothly. And orchestration will make sure that all of our services which are running as a pods will be up live all the time. If there's a need for scaling up or scaling down, it should be there. So all those things will be taken care by the Kubernetes as an orchestration engine. Then we have a data layer. So in data layer, we are using Cassandra as a database in Cassandra. And we have a gateway through which you can access your data. And the gateway is called as a Stargate. What is a Stargate? Gives you a flexibility. Why we use this data gateway? Why we are not directly accessing the data by accessing? Stargate gives a flexibility to us to access the data in a model we want. What model means? If we want to access the data using a REST APIs, if we want to access the data, read or write the data using the JSON, we can do that. And if you want to access the data using the Graph API or something, we will be easily able to do that. And then at the top, nowadays, where this data is used, or who are the sources of the data. The most of the time, the sources of the data are the mobile and the web apps. And all those mobile and web apps nowadays are moving toward from monolithic approach to the microservices, because it gives the flexibility. It improves the development process. It gives the speed. And same way, if now our database can also run as a microservice on top of a Kubernetes. Now, first, I told you I will give a very short introduction about Apache Cassandra and also a very short introduction on Kubernetes for those whom the Apache Cassandra and Kubernetes both are new. I will not cover so much detail about both of them, but yes, a little bit knowledge so that whenever we are going for some workshop or a deployment, you will be able to understand what I am talking about. Okay. Now, what's a Cassandra? The Cassandra comes in a category of a NoSQL database, or sometimes we also call them as non-relational databases. So whenever the NoSQL comes, we say that not like a SQL, they don't have. So if SQL, if we say it's a structured query language, so it's not, it's like a misnomer. We have the query language to query over data. So here we call it the SQL, but we also have some different interfaces also to connect to the data. I told you using REST API, JSON, and all those kind of things. You can read your data, you can query your data the way you want. So what is NoSQL? NoSQL is a distributed database. And what are the differences between traditional and distributed database? There's a very simple, if I talk about, there's a very simple difference. If I have to do something, and if I work for 9 or 12 hours to do that thing, that is a single system. I am enhancing myself. I'm scaling myself for doing some task from 9 to 12 hours, scaling by 3 hours. That is single scale up system. But what's a distributed system? If I got some task, and if I add one more team member in my team, and we will distribute the workload, that is a distributed system. The same thing these distributed databases does. So whenever the data increases, because nowadays the data is increasing so fast, and our traditional databases are not able to scale or perform in that circumstances. So what NoSQL gives a power? They can distribute our workload. So that means we don't have a single server serving our purpose. We have multiple servers which will be there, which we call them in Cassandra as a node. So node can be anything. It can be any JVM process which is running the Cassandra service. Okay, it can be a virtual machine, it can be a Docker image, or it can be a physical server, or what I can say that bare metal server also. Okay, so nodes will be there. So what happens in a distributed data systems? You have a scale out architecture, and performance will not be compromised. For me, the definition of the scalability is ability of the system to expand with growth in demand, keeping the performance in check. And this is what NoSQL distributed database are helping us. Because whenever there's a load increase, you can add more nodes, they will distribute the load, and your performance will not be so much compromised. And Cassandra has a ring-like architecture. What's a ring-like architecture? Every node is communicating with each other, and every node knows about each other through the gossip protocol. They keep on sharing the information with each other about the token exchange and everything using this gossip protocol. And using this gossip protocol only, they will be able to know that which node is active or which node is dead, so that if there's any failure, they will be easily able to handle those failures. So this is what we have as a NoSQL database, Apache Cassandra running as a ring. And I told you the load will be distributed. So what is the load here? The load here is both the things, data and the query. So data is stored across the nodes in the local disks. We prefer the JBOD disks, the disks which are attached to the server. So now if I go one step back, if we have a data like this, a country, city, and population, and I need to store this data. So, and this data is a huge amount of data. I have a data for the complete world, and I need to store it. You know how many records will be there. So if I'm storing it, I can distribute that data across the number of the nodes. So for example, now this data is distributed across multiple nodes in this ring-like architecture. The US data goes on one server, the Denmark on one, UK on one, Indian, Australia on one. So all those kind of data we distributed across these servers. And how we distribute the data, how the data will get distributed. Does it get automatically one record on one node, another on another? No, because there's a strategy. And one of the most important point of that strategy of distribution of data is a partition key. So here, if I go one step back, the partition key is a country. And now the partitions are getting distributed across the servers. There are chances when multiple partitions can be on a single server, or all the partitions can be distributed across the servers. It depends upon a load, because we want, or Cassandra, what it does, it will keep the same load. It will try to keep the same load across these servers. And now this is the one thing. Now, whenever we talk about Cassandra, we say Cassandra is highly available, distributed, fast performing database. No, you have seen the two things. The data is distributed, and Cassandra is a highly scalable because you can add up or remove nodes at any point of a time. So what is missing? Highly availability. So how we achieve this high availability? That is achieved using the replication factor. So replication factor means nothing. It means simply how many copies of the data you want to keep. So if I say replication factor 3, then I need minimum 3 copies of data. Then what is my high availability? My data will not be lost if I lose 2 nodes, because data is lying on the 3 nodes. Still I am having the 3rd copy of the data sitting on some other server. So that is what we mean by data is replicated. Is that clear? So for example, this is a 59 data. So it will be replicated across. So whenever there's a read and write, the read and write request will come to the coordination node. And then from the coordination node, it will go to the nodes based on the token topology. I'm not going so deep into it based on the token numbers or something, hash numbers. It will go to the different nodes. And you are seeing this data is replicating across the 3 different nodes. So this is here. And what happens if one of the node is down? When it has to write the data on that node, then the coordination node will store a hint for that this data was not able to get written on the 3rd node. And whenever that node will come up, automatically the data will be written there also. Is that clear? And whenever the node will come up, the data will also come there. And what will be topology? See, whenever we say that we have to keep the data distributed, we work on different things. For example, we have to work. We need to make sure if we are in cloud, there will be if single availability zone is going down, still we have the access to the data. Or if single region is affected, we can have the access to the data. Or if we are in our local data center, we want to keep the RAC awareness, or we want to keep the disaster recovery and all other kind of things. So if we want to keep the disaster recovery, we should store our data across the data centers. And if we want to keep a high availability and protect our database from going down in case of the RAC failure or the availability zone, then we will spread our nodes across different AZs or different racks. So this is what we should do. And the data, so we are keeping some nodes on rack A, some on rack 2, rack 3. So if single rack goes down, still we have 4 quorum of nodes available there. We are able to take all the read and write requests. So this is what we need to make sure. So next step is that data will be distributed. There will be a geographical distribution of the data. So not only you can keep the data at a single data center, single city, but you can distribute your data across different geographical locations of the world. You can have some of your data sitting in India, some of your data sitting in Australia, and some of your data sitting in Singapore. For example, you want to keep your data, what I can say, durability across the different regions. And you have the users which are accessing the data from these 3 different geographical regions. Same way, the Cassandra not only gives you flexibility of different regions, but also different cloud providers. You are having some applications which are running on GCP and some are running on Azure, and you want that data should be spread across both the data centers. And then you also have an option of deploying these rings in different data clouds or different data centers. Okay. For example, I will give a quick reference how scalable we are. So all of you may be watching the videos, the series on Netflix, and all that power to that, what I can say, what you are streaming is given by the Cassandra. And we are running 10 and thousands of Apache Cassandra nodes. We have a huge amount of data which is distributed across the Cassandra nodes and which is spread across the multiple AWS regions, because Netflix has the users across the geographical zones, and Netflix need to be up always, and the data should be persistent there. So all those things, all those power to Netflix will be given by the Apache Cassandra as a database. Same way, Apple, all of you know, we all are using Apple products, and Apple also for his, what I can say, Pay and other applications use very big clusters, a huge size of clusters. They have almost 160K nodes in one of their clusters. They're running 160K Apache Cassandra instances, and they are having the data more than 100 petabyte, and their requirement is of million operations per second. So that is how they are getting the scalability performance. That is what I talked at the beginning. Scalability is not expanding or growing with the demand. Scalability is growing with the demand and keeping the performance also in check. And that is what you are getting with the power of a Cassandra. You're not only getting the more storage to store the data, but you're also getting scalability in terms of the query. You are able to run the query with the same SLAs, with the same performance. Even your data increases by adding few number of nodes, just like plug and play kind of a thing. Okay, so what is our task today? I'm here to show you how these nodes will get deployed as a pods on the different Kubernetes nodes, and how we make it very simple with our operator to deploy all these how to deploy the complete Cassandra cluster on the Kubernetes. So now, if I ask you to set up a Cassandra cluster, so what steps you will do? You first need to set up a networking, storage, firewall limitation. Then you need to install the Cassandra on all the nodes. Then you need to set up some monitoring softwares and all those kind of things. Then you have to configure your backup, repair, and all other kind of policies, or you need to install the agents. Sorry. So there are a lot of things which you need to do. Lot of things. So how we are going to see how we are going to deploy. So we will take a lot of time to deploy. So let's not do all these things. Let's do it very quickly. So first, let me introduce Cassandra. So Cassandra is something which is developed by DataStax, and then later it's open source to give the developers or give the administrators flexibility to deploy the Cassandra on the Kubernetes. So you can deploy the Cassandra on any of the, what I can say, that cloud or in-house using this Cassandra operator. So first, what I will take you through. Yeah, I know that you don't know some of the basics. We don't have gone through some of the basic concepts of the Kubernetes, but I'm saying that let's set up the Cassandra. So let's quickly, what I will do, I'll try to wind up some of the basic points about what I can say that Cassandra, what I can say that Cassandra components and Kubernetes, and then we will quickly go and check each and everything. So what is a Kubernetes actually? Kubernetes is running your app. Kubernetes is an orchestration service which will help you to run your application on the nodes as a container or a pod. So one of the smallest unit of what I can say that Kubernetes is a pod. So pod is nothing, it's a namespace or a service which you are running. Am I right? So for example, if I'm running one service, I can run it as a pod A. And if I'm running a service B, I can run it as a pod B. And inside the pods, we can have one or more containers. Most of the time, you will see only single container running on the pod. But even if you want to distribute something inside those containers within a pod, you can do that. But the pod will have the single IP address. The containers inside those pod will have the same identity as a pod. They will share the IP address, they will share the namespace, they will share the storage, they will share each and everything with each other. Most of you will be already knowing about that, what's pod and all those kind of things. Second point, which I want to configure is that some of the storage terms, because we are going to deploy the database on Kubernetes, and database means data. And we will not be saying that once I will terminate that pod or something happens, the data should get lost. We need that data always because it's a database. So we need a persistent volume need to be attached to a service, to a pod. So what's a persistent volume? Persistent volume is a volume in which your data will not be lost, even if your pod got terminated or got killed. So this persistent volume can be anything, because there will be a storage class. You may have different kind of a storage like NFS, storage class for some object storages, storage class from some NAS storages, or different kind of things. We have the storage classes also for different cloud providers. For example, Elastic File Share for the Kubernetes, we create there some file shares, and then we share those file shares with the pods and all those kind of things. So there can be different kind of storage classes. And then in the storage class, what we will do, we'll create one PV, which is called as a physical volume. Physical volume is nothing, it's like a volume. It's, if I say simply, whenever you need to add a disk to your server, in a normal cases, you add one volume to your server, we also call that as a physical volume. So physical volume is nothing, is a storage container inside which data will be stored. And this volume, this will be the data. And then what's a persistent volume claim? So persistent volume claim is a service which will connect your namespace to that persistent volume. So it will take all your requests, user requests, or a pod request which is coming for storing the data on the PV. It will take all those things. And if I want to make it simple, see, for example, in the traditional infrastructure or in a VMware, what we have the CUSY protocols using which we will write on the disk the same way something this PVC also does. Not exactly, but you can get an idea how it works. Okay, and then what's the stateful set? We will be talking a lot about the stateful set. So stateful set is a set of pods which have the constant identity. That means their state will not change. Even if there is what I can say that any issues with the networking or your pod will come up again to do some failure, it will come with the same consistent identity. Same host name or something, whichever you have given to that. Okay. So some of the custom resources or configurations which we give whenever we create because we have to create those YAML files or configuration files, what we give them. So if you see this sample file, I'll show you one more sample file from when we will do the actual deployment. So you see that here. So first we give some API version. This is an optional. So we have a kind. So what we are doing, kind is this kind of service. It can be a service, it can be a pod, it can be a stateful set, it can be anything. So here what our kind is, we are defining the custom resources. For example, we are saying the name of the cluster will be this, group will be this, and then we are saying the Cassandra data center. So Cassandra data center, what this kind does, actually it is our CAS operator. And what does our CAS operator does? It will help you to deploy your Cassandra cluster. It has all the services, information, everything there. And whenever you say for the Cassandra deployment, it will deploy all those processes like repair services, matrix collector, all as a pod in the Kubernetes cluster. Okay, so you have this. We will have the backup and restore services like Medua, and we have the repair services. We will have the Grafana for the what I can say that store for the monitoring and all those kind of things. And this is something how we define all those services. Okay, what will happen? So this will be operator, and this operator will connect to the Kubernetes API, because you know that in the Kubernetes master node or Kubernetes for the cloud or also anywhere, we have some API services, we have the database in the etcd, we have the scheduler, we have a master, we have the we have a lot of services which will be running. We have the kubelet on the nodes running, we have the proxy proxy running on the nodes. So all those different kind of services are running. So what does this operator do? It will talk. So what does this operator will do? Operator will have all the information what need to deploy, and then it will deploy all those services on the cluster, and then all those stateful sets will be deployed on the Kubernetes cluster using this CAS operator, because CAS operator has the information about all those services. Am I right? And then it will be monitored, the states will be monitored, and if any pods go down, it will automatically try to recover that. And this will be for this single namespace, which is called as a cluster. Is that clear? Okay, so with the help of Kubernetes operator, you will be able to define what kind of a services developers can give their own information to the cluster which should be created there. Is that clear? Any questions? Any questions? So we are moving to the next step. You can post your questions in the chat, and the team will try to answer all of those questions. Okay. So first, we will have the Kubernetes master. We will be having the worker nodes, and we have the container D or Docker D or any kind of a service which will be running there. I told you that we have the kube proxy for the networking. We will have the kubelet which will talk to the master for deploying all those pods on the different container, different nodes. Is that clear? So what we're going to do? So if we have the normal Kubernetes stuff, we need to do all those things. I told you, you need to install the Cassandra, you need to set up storage and everything. This will be a very tough task. So what we do, we make it simpler for the deployment. So what are the CAS operator features? What does CAS operator gives you? It gives you a proper token ring initialization. It will help you to decide the seed node management and all those kind of things. And it will do the server configuration, integration into the different data centers. Rolling reboot of the nodes if there's some change in that complete state set, if I say that. And it will store your data with the rack awareness with the pod running on the different nodes. Okay, it can scale up and scale down quickly. So all those kind of things will be provided you by a CAS operator. And if CAS operator is not there, then you need to do all those stuff manually. So this is how we have the CAS operators there. Okay, let's quickly go for some hands-on. And I created a very simple start for those hands-on. So when I say that setting up a Cassandra, so most of you have joined this meeting on using your laptops and all other kind of things. You will not be having a lab environment or some servers. So very simple to start deployment of the Cassandra on a Kubernetes is you should have Minikube installed on your laptop for your desktops. Then you will have kubectl and Helm. So there are very simple links to which you can go. You can simply type install Minikube, install kubectl, and install Helm on your web browser, and they will take you to these links. And on these links, using these links, you can quickly install all the three softwares. I've already did it for mine. I already done for mine. So after installing, what we do, I will keep what I can say that my shell ready, so where I will run up these commands. I hope you are able to see my shell. So now what we are going to do first, because we're going to create a Cassandra cluster, we will test these some scaling and all those kind of things. So we'll start the Minikube with more CPU and more memory. Usually it starts with default 2 GB memory and 1 CPU kind of a thing, or I think 4 GB memory or 2 CPUs. But we want to start it with 4 CPUs and memory of approximately 8 GB, so you can start it. So this is the first start you think you should do. Okay, so Minikube start. So I think it's already running for me. So let me check. Okay, yes, it's already running for me. So my Minikube is up and running. And next thing, what we will do, we will check the storage classes. Why? We have to attach a persistent volume, and we need to keep that data safe always on the cluster. So we need to check also that persistent volume storage class is there or not. We talked about the storage class for some time. Most of you, if you are doing it for first time and you are trying this Cassandra deployment on the Kubernetes first time, you will not be able to see this Ratcher IO local path. Waiting for first consumer, you'll not be able to see it. So what's a way to get it created? So I've given the command. So you can do this command kubectl apply, and you can create this path also if you want. Okay, so quickly you can run this command and you can have that particular storage available there. And then you need to get the repos for the Cassandra. The repo will have all the information related to the cache operator, all those services which you're going to deploy. Everything will be there in the repo file, in the repositories which you will do. So what commands you will usually run? Help repo add K8 Cassandra, or you want to give some other name you can give, and then you have to give a location where that repo is available. For example, here it is given this location, so I can copy paste quickly and then I can paste it out there. So for me, these repos are already existing there, but to show you how to run this command, so it says that already exist. And if you have done this spectacle earlier also, you tried this, what I can say that this earlier also, you can see that these repos, sorry, not Helm repos list. So you can check out that your repo exists or not. Sorry, a typo by me. And it says that already I have the two repos, which is Cassandra and which is traffic. Now what this traffic repo does? Traffic will help you to access your the Cassandra cluster or Cassandra Cassandra cluster Cassandra services which are running on the Kubernetes on your local machine. So it will do some kind of a routing or port forwarding for you to access those services on your local machine. So that is why they are very important. So instead of directly reaching to the network of a Kubernetes pod, you can access using them, their local host. You can do this using this. And after you added these repositories, you have to run the Helm repo update to update your repositories. So you can do quickly by this. Okay, so it got all the updates for your repository. Okay, this was done. It was very simple. So what we are going to do? No, we are going to do the deploy the Cassandra. So let me show you something. So already I pasted, I have a sample file. So what I'll do, I think I have some Cassandra YAML file here. If it is there, I'll take you through that quickly. Yes. So this is here. So cassandra.yml file we are using for the deployment. And what I'm going to deploy, Cassandra as a service. And what version of Cassandra, you can choose a latest version also. And what is a storage class, local path. And I'm giving a 5 GB of storage because we are just creating it for a testing purpose. Do you want to allow the multiple nodes per worker? Yes, we can do it. A single worker node of the Kubernetes, do you want to have multiple pods or things running inside it? Yes, because in a local desktop, we can't have the multiple machines. What will be the heap size? You know that Cassandra is a Java process, so heap is very important component there. So we are giving a heap size of 1 GB and new generation heap size of 1 GB. So then we are giving some CPU and memory, and we are setting some limitation for the CPU also. And then we are giving the data centers. You can here define the multiple data centers also if you want. If your Kubernetes nodes are spread across the multiple, what I can say that pods or something like that, you can give that also. Okay, then for the monitoring, we have a Prometheus tag, and we are giving some default username and password for it. And if you want to change that password, you can give that password also here. If you want to set up some password, and then we have I can also give you the command later on if you want to change the password, or somebody forgot the password after changing first time, how it can be done. Then we are also enabling the Stargate API. Okay, and how many Stargate API replicas we want to run? Because it's a single node, so 1, and I'm giving some heap memory and some CPU limitation to this Stargate API also. Because I told you everything will be run as a different service here. We are dividing all those which are running inside a same JVM container into some different processes here in Kubernetes. Okay, after this, it's very simple. So I'll copy paste most of the commands to reduce the time taken for running these commands. So you can do helm install -f cassandra.yml Cassandra. You can give here your cluster name. So your cluster name can be anything. I'm giving the same Cassandra for time being, but if you want to give some demo cluster, cluster 1, or my cluster, it's up to you. You can give any of your cluster names. So this command is simple. It has install using this file. Whatever mentioned in this file, use that for installation. Use the Cassandra repository which we have created, which you have seen from Helm repo list. And then also we are saying the name of the cluster which you should use. So after that, we'll press the enter. So it will take some time depending upon the resources on your system. Usually it is quick for me. Let me check. Yeah, it's deployed. It's deployed, but it's too quick to check the statistics of all the pods. But I'll show you how the statistics should be running. So there will be one service which will be completed, but most of this default STS services should be 2 by 2. There should be Stargate API which should be running, and some of the services this is a repair services which is repair pod. This is Cassandra Prometheus for monitoring pod. This is a Grafana pod which will have the dashboard. This is a data center 1 pod which is running the service. This is the upgrader which is completed, and this is a CAS operator which is running everything, which is a mastermind of this. So this is also running. So if I check in sometime again, it's there. So most of the things will slowly move into the running status or 1 by 1 status. We'll wait for some time more and things will look more, but I can say that prominent. Now I will also check the health of the cluster which I am setting up, and quickly my motto is just to show you what are these commands are running. So we have created one cluster. We will define the Cassandra data centers, and data center 1, which was mentioned in the cassandra.yml file, cassandra.yml file, that data center 1 is running from 87 seconds. And let us also check for the data center 1 how our CAS operator is running. So we can go and take this here. So its CAS vendor is ready and ready to work, and then we will check how many services are up and live. Simple running of this command will help me to get that. So you will be able to see this, how this is running. All the services are running. There are some cluster IPs, there are some ports which are associated to it. All those things are running here. Is that clear? Any questions? You can put it on chat, but here how we deployed our compute Kubernetes Cassandra on the Kubernetes. No, it is deployed. Does it work or not? Let's see. Does we are able to connect to it? Does data is getting persistent on the disk or not? These are still the questions, but clusters is up because I am able to see the most of the pods is in running state. or they are able to run, because this was important for me. It's running. Stargate is about to run, because using the Stargate, I need to connect to the data. I need to connect to my cluster and do some read and writing of the data. So this is also very important for me. Grafana dashboard, I can do the monitoring now. Repairing, still it is in progress. It will take some time. And it depends also on the power of the machine, how quick everything will be going to come up. Okay, this is done. So this is done. This was a sample Cassandra.yml file which we have used. Now I'll go to the next step. So what we have done, we have run the traffic for the Kubernetes ingress for external access. We have the Stargate, which will be what I can say the default gateway for all our kind of queries, connectivity, read and write. Then we ran a Cassandra via CAS operator to scalable cloud native database. We have the repair Medusa as a service pod running. And then we will have the pod running for Grafana and Prometheus. Most of you know that Prometheus is used for collecting the metrics, and Grafana gives us a beautiful dashboards to see those metrics. So it makes visualization very good for all those metrics which are collected by the Prometheus. And yes, this Helm guy is very helpful, because using this, we are easily and quickly with the simple commands are able to deploy our cluster. So this is how our cluster is getting deployed. Okay, so we have a traffic, gateway, metrics, UI, microservices, and Cassandra NoSQL. And we have the Medusa services for backup and repair, which can take your backup to the object storage and then restore it back from there. You have the repair services in Cassandra. Sometime when the nodes goes down, that node will have the delayed copy or will not have the actual copy of the data. So what we want to do that? So what we want to do there? We want to do the repair on the nodes. So that repair will be taken care by this repair services. So all these things are running as the microservices. Okay, and to connect to these microservices from the outside, we are using this traffic ingress here as of now. Okay, so most of the things here I already explained to you, something like that. We are already seen. Now what I'll do, I'll show you how we will monitor our Cassandra. Let us deploy. Does it run or not? Let's see. Okay, for monitoring also you will see your dashboards like this and all like this kind of things. But let me show you how we will enable that. The first, using that traffic operator, we will forward these requests to over what I can say that we will forward over these requests to the what I can say that to the local host. So this commands need to be copy pasted. Let me get the statistics one time more. Most of the things are running now. Yes, they are running, they are up and running. All those important services are there running. So first step done. And then I need to do the second step also. So I need to take this, what I can say that out. So quickly. So this is a change in my version of the Cassandra, because I did some changes in the cluster, and you can see this. Now who will be here? Because it is rolling out the statistics. If you do kubectl pods, still you will not see some of them the ready, or most of them will be ready. So now if I do kubectl get services, okay, so I am seeing that my Grafana is running somewhere. Oh, it's running here. It is running on the 80 TCP port. So what I'll do, I'll quickly forward this to some other port. Why? Because I want that to connect from there, because in my system, I don't know why this port is not, or ATT port is not coming up. I don't want to troubleshoot it. So I know that I can port forward this. So I have forwarded the request to different port. And let me do, so which port I forwarded? 7500, yes. And why I'm giving this? So let me do 7500. So what is the username? Admin. And what is the username we have given? admin 123, I think so. It's not taking it. So in the file we've given admin and admin 123. Let us see that file again. That is admin and admin 123. Yes. So yeah, the password was admin and admin password was admin 123. It didn't take it sometime. The default password usually I mentioned there is a secret. It takes that. Okay, so I given the secret, so it was able to take that. You can click on the dashboard homes and you can go to the dashboards. You want to see the multiple dashboards, you can check here and you can see the Cassandra cluster and services which are there. So we are seeing the node is down. Maybe it is taking some time to come up. Okay, let me check why it's down. One second. Push. Tab. CTL get bots. It's running. It's running. It's completed. Target one was not running and one is running. Let's see what's happening here. So this is how you will get your dashboard. Let me check. So this will be your request, how many reads are coming, throughput, your read latency, see your node status. Node is up now and the node count is 1. You are able to see total count is 1 and the disk you are using, what is the disk space, the different files which are using inside that, it's given there. As of now, any compactions are pending on the table. It is also shown here. Any errors in the throughput, everything will come up here in this beautiful dashboard. Apart from that, you can also check the statistics for your Stargate API. I don't want to make any changes. So any HTTP request, JVM heap usage, which is happening there, you will be able to see from here. You have the system and node metrics. So CPU busy, memory used, swap used, disk used. You will be seeing a little higher for my system because this is a simple desktop on which I am running the service. How many cores are there, how many RAM and all those kind of on the local system and everything it is giving to me. Okay, because you know that why it's giving 8 GB because I started this with the 8 GB system load and system uptime. So everything is given there. So it's my node on which this thing is running in Cassandra overview. And we have also the condensed dashboard, which is there. Okay, so this is all how you have the different SQL clients, request, compaction. And now after this, what we will try to do, I will tell you if you want to try of your own also, you have this Cassandra.io available here. Using this Cassandra.io, you will get all the documents which are there. Before I will move to the next workshop to connect to the database and all other kind of things. So you have this, what I can say, that Cassandra.io there. You can check all the documents from here, getting started. You can do small basic hands-on if you want to do on any cloud provider or on your local system. The docs for everything is given here. So you have blogs, all those, whatever the events we are doing related to the Cassandra, everything is covered in this Cassandra.io. Okay, let's see the third thing. We also want to see some write, read, or do some data, kind of a data thing with this thing. So let's see how we are going to do. So now I'll try to run this command to do the port forwarding. Okay, for that, let's do that. What I did, I have run this command and did a port forwarding like this. So forwarded from there to the 9042 because I want to connect to my system. So next step, which I'll do quickly, this is a simple command to do the port forwarding services. I did this port forwarding from 80 to 7500 also sometime before, but now I am doing this forwarding from internal 8080 to the external 8080, 8081 to external 8080, and you know that our SQL will work on the 9042 port. So that means now if I want to connect to that, I can use that for the connectivity. Now let's go to the next step. So what I need to do? Now I will use quickly the SQL shell to show you how you can do the quick connection to your Kubernetes cluster. So let's see how we are going to do that. Okay, so what is here? So I'm coming to this here. So what I am doing, first to connect to the cluster, I need a username and a password. So what I'll do, I'll quickly get the username of the cluster which I have deployed. So these commands will help you to get the username and passwords. So user is Cassandra super user, and we will now get the password also quickly. So let's see how to get that password. It's a single command, getting the secret. You can put both the commands together in the, what I can say that, script, and it will give you together the result of what I can say that username and password. So once I was able to get this username and password, now I will be able to connect to my cluster. But for connectivity, you need the client. Either you need to use the REST APIs to connect, or you use the JSON, or using those target and all those kind of things. I told you that I will show you a SQL SH. How you will be able, because for the REST APIs and other the commands are given very simply, which are very simply available on what I can say that on our Stargate.io. So how we are going to connect to this SQL SH? It's also very simple. So first, what you need to do, you need to download the SQL SH for Extra, which is available on the DataStax website. Once you do download, you can, what I can say that, unzip that. I've already unzipped that, so I'll go to the folder. Quickly doing this SQLSH.extra, and you know that this file, I didn't set up a path. I'm a bit lazy in doing that. So you know that in bin folder we have most of those things which are available there. So we have the SQLSH available there. Now after generating that username and password, we need to go for that. So SQLSH minus user. So what username we got? We got some username. We got a Cassandra super user. So let's copy this. So quickly I'm copying this, and then I need to give some password also. Let's see. It wants the host also. So host will be, in our case, we will do localhost. Okay, the password requires an argument which I need to give, which I am missing. So password is also I generated somewhere. But copying a password, you need to be a little bit careful, because if you copy the white spaces, then this password is going to give us trouble. So that is why I put it in there. And I think I'm not copying any white spaces. Let's check it out. Yeah, see, I'm inside the SQL shell inside the Cassandra cluster. So now we are sure, we are sure this Cassandra is running on Kubernetes cluster and it's running there. So we are inside the shell. Okay, and then what we are going to do? We can do describe key spaces to list our key spaces or something which we want to do. Okay, so all those commands which you want to do, you will be able to see from here. So you want to create a table, you want to see something, you can do this here. Okay, and all those documents related to your SQLSH command is available there. So this is where you can get your SQLSH commands which you need to run if you're a first time user and you're doing first time. There will be some little differences between the commands of what I can say that which works there. So you can see here. So you can see we have a describe cluster. So this is a describe cluster you can use, or something describe cluster or disk cluster. So it will give you about the information about your cluster, describe cluster, and all those informations you are able to get. Okay, so we are running the cluster Cassandra. if you remember that we created a cluster with a Cassandra, and by default it is using the murmur partitioning. Okay, so this is how you will be easily able to access. After that, if you want to create a table, you want to, what I can say, that you want to create a table, or you want to create anything, you will be able to do it using that. Okay, any questions, any queries, you can paste it on a chat. Apart from that, I will quickly want to take in the last 5 minutes through some of what I can say that important concepts. No, you already know the Cassandra. You can quickly do the read and writes if you want. You're connected to the cluster and all those kind of things. And also, what else we can do? We can quickly scale up the cluster with a single command instead of bringing up the server, doing all those kind of things. We can be easily able to set the size equal to 3, and we will be able to see the Cassandra cluster getting provisioned with the 3 nodes. And you will see the 3 pods which will be running there for the Cassandra cluster. So this is how you can do and we have a different service for repairing and all those kind of things. But what best practices we should follow? The best practices which should be followed for the high availability, scalability, and performance, you should have some good disks for the persistent volume, where the cluster is able to persistent the data much faster. You have your backup services configured, because backup to the object storage or a shared storage, because you know that these containers or these pods are volatile in nature. And also you should have multiple node Kubernetes cluster to give it high availability. If it is a failure of a pod, and then it is okay. But if it is a failure of a node of a Kubernetes cluster, then your services may get impacted. So that is why whenever you're running these kind of services, you're running it for a production, try to have multiple nodes running these particular Kubernetes services, which was defined in the picture. Okay. So with this, I would like to say thank you, and over to you.
Okay, good morning, good evening, good afternoon, good night, everyone. Happy to be with you for this hour and introduce you about a great tool to build an open source API layer on top of Cassandra. I'm Cédric Lunven, and I'm leading the developer advocacy team at DataStax. So as advocate, we do training, public speaking, support the developer, building some tools, sample code, sample apps, and doing some talks and presentation like today. I'm a Java geek, so expect some Java code, probably a little bit of live coding in the end. I did some Spring for a couple of years already, and let's jump into it right away. So today's 6 parts, I will explain you what is a tool. It's called Stargate. Then we will explore together what are the available APIs for you. So REST, document-oriented, to use Cassandra as a document-oriented database. Yeah, that's quite innovating. GraphQL, the new way to expose things. It will take over probably all the APIs in the coming years, I think. Just so much value. Then all about the toolings, because it's cool to have those APIs, but you want to use them. So you should not have to read the specification and build the tool by yourself to consume the API. And then we will go to what's next. Okay, so the idea is first, we would like to avoid a developer to know all the languages. You know, as a developer wanted to use a database, you need to know the language of the database. If you are using JDBC, you need SQL. If you are using Cassandra, you need SQL. If you need Mongo, you need to know JSON-B. It could be N1QL if you're using Couchbase. Yes, there are a lot of language to know when you deal with the database. So that's first things. And second, it's a binary format, and most of the time it needs to be stateful, maintaining some connection between you and the database. So the idea is to provide a data gateway, a proxy on top of your database to expose APIs and allow stateless service on top of the database. So developers would like only to consume APIs, especially if they are front-end or mobile developers. Cassandra is a database designed for the new standard associated with APIs. Yeah, with microservices, we tend to say, yeah, it's one database per microservice. Well, not really. It's not really how it works. What you want to do is isolate the microservice as much as possible. And with Cassandra, you can do that. You can isolate per cluster, per DC, per key space, and even per table. So it's super fitted to be used on top of microservices. Okay, so the product, the tools called Stargate is just that, an open source framework for data, a proxy on top of the database to consume your data and expose some APIs. So this is a project, Stargate.io. It has about 2 years, and you can see we do have about 500 stars on GitHub already, more than 30 contributors, and it's in heavy development by DataStax, but we are looking for contributors. So it's a proxy. So it will introduce some loose copying between the database and the APIs, and we will have at the bottom the persistence extension, and at the top the API extensions. Persistence extensions, multiple versions of Cassandra as of today, 3x, 4x, and everything related to DataStax Enterprise. Okay, so multiple versions of Cassandra, and at the top, multiple flavors of API that I will cover in details during this presentation. Data, GraphQL, document, and SQL. gRPC will be released next week. So this is our big proxy here. So it's an OSGI application. So it's based on Java, OSGI, and the framework implementing the OSGI is Felix. This is our runtime. Then to expose API, we are using the Java framework called Drop Wizard. This is the hat logo that you can see here. And you expose one API on each port. So 8080, 8081 for the authentication, 8082 for the REST, 8090 for gRPC. To use those services, you need to authenticate. So you do have the endpoint auth here at the top left-hand corner to get you a token. And the token will live for by default 30 minutes. You can say you can set the time to live for your token. The token is crypted and stored on one of the Cassandra table you are using, just to check on that in a technical dedicated key space for Stargate. Then it's all about filters and services. OSGI is all about services, so authentication services to see if your token is valid when you invoke any endpoint. Then rate limiting, just to throttling the request as an API management solution. You don't want to overload your system. And the persistence service, which is an abstraction on top of Cassandra. So as of today, it's Cassandra only, but the way Stargate has been implemented does not prevent you to change Cassandra by something else. It's just a matter of implementation, just a new storage for the Stargate. That's really, the goal is really to introduce these multiple persistence. Okay, it's an OSGI layer. Also, Stargate expose here a metric server on 8084. So the metric server is really by default provided by Drop Wizard. And this metric server could be consumed by Prometheus, for instance, the Prometheus service monitor. And you can draw some nice dashboard in Grafana. And here, one step even further, you can see that even for the API REST, you do have multiple services, but we will see that GraphQL the same. Here you do have the full pictures of what you find in Stargate. So first, authentication. Okay, Stargate is not a single point of failure. Of course, you would like to scale out your Stargate layer, and what you need to do is having a load balancer on top of the Stargates, and with that you are able to use any REST API. So the authentication is no different. You really want to have multiple Stargate to avoid spoof, and each Stargate can expose the authentication API. So you just provide user and password, reusing the role-based access control from Cassandra. Not reinventing the wheel here. So you can set up some dedicated role at Cassandra level to be exposed by Stargate. That's the best practice. The token by default is 30 minutes, but you can extend or reduce that time. And the token, of course, are shared by a table in Cassandra between multiple Stargate nodes. So you don't need stickiness to use some Stargate node. I told you that Stargate expose some metrics endpoint. So those are sample dashboard in Grafana based on the metrics we collect from the Stargate JVM. Stargate is used in production by DataStax on AstraDB, which is Cassandra as a service in the cloud. And we provide on top of Cassandra the Stargate APIs. So those are dashboard that you can find in the Astra dashboard. So this is the JVM, HTTP traffic. So see all the requests with the throughput and the latency. And you can see, you do have here a dashboard to see, hey, for each node, how many codes do we have, and how much time, what is the latency for each endpoint, so authentication, REST, and GraphQL. Okay, so before so I totally expect you to have some knowledge on Cassandra. So before, when you need to log in and connect to Cassandra, you provide some contact points. One is enough for the first call to get the full topology of the cluster. Multiple is better. And in your application, you will use the driver, and the driver will open and maintain some persistent connection between the nodes, because the driver is clever doing the failover, load balancing, health check for you, and is token aware. So the driver will connect and retrieve the data from the proper replica based on your request. To do all these magic, the drivers need to keep those connections open, so it's totally stateful. And if you do have a large number of nodes and maybe multiple instances of your services, because you are working now on microservice, that could be costly to open so many connections to connect to your cluster. But it was before Stargate. Now with Stargate, this proxy, not only you still have the SQL to connect to, but also the three, for now, stateless endpoint, GraphQL, gRPC, REST. Stargate itself is a Cassandra node without any data. And it's pretty clever, because with that, the Stargate node here in yellow can join the gossiping of the Cassandra cluster. So the Stargate is token aware, and it will act as coordinator node for your request. So with that, you can keep using the consistency level. Everything would work the same with or without Stargate. Now, I told you Stargate is not a single pool of failure. So what you want to do is have multiple Stargate and put some load balancer on top of Stargate nodes to do some stateless load balancing. I told you there is no stickiness. So that's pretty cool. With that schema, you can notice that you can scale the Stargate layer without scaling the data. Before with Cassandra, if you need more if you need more capacity, you have to add new node. But if you need more throughput, you also have to add new node. Sometimes you add new node just to improve the throughput, including disk, where disk were not really needed. Now with Stargate, we split the compute and the storage, and you can only scale the compute layer if you want to do so. Okay, pretty amazing. So I gave you the overall architecture of the proxy, but let's have a look of what is available. And let's not do only slide, but let me show you and play a bit with it all together. So the Stargate REST API, so-called REST API, is really a way to expose all the features that you can do with the Cassandra query language as REST. So you find the same keyword, key space, table, colon, user-defined types. So if you already know Cassandra query language, you won't get lost. Okay. Not only Stargate provides the endpoint, but also the Swagger definition or Open API specification. And by just starting the node, you will see you can access the web page and start using the API using the Swagger. So 2 parts in the Swagger API, and you will see that you will find 2 parts in most of the API. One is for DDL, so data definition language, so all about the schema over here. And the second portion is the DML, everything related to data. So working with row, add row, retrieve rows. It's of course recommended to query by the primary key, because hey, this is how you work with Cassandra. We also put some dedicated endpoints to retrieve all the rows, but you still have to provide the partition key. Otherwise, you need allow filtering, and it's super slow. of course. Okay, so enough me talking and only slide. Let's have a look of what we can do. So if I move to my here screen, I do have a GitHub repo for you. So let me copy the GitHub repo for you to bookmark. So copy that in the chat right now. And there it will explain how to start a Cassandra node and start some Stargate on top of it. So how to install Docker, how to install Docker Compose, how to start the demos, so cloning this repo, do some Docker Compose up. In the instruction, you will start a 3-node cluster with the key space and replication factor 3, and you will get 1 Stargate. So that's overall 4 containers to run. Okay, so you can see here what it looks like. You can also, and this is what I will do today, go to stargate.io. Okay, just stargate.io. So let me also ping you here like that. Go to the documentation, pick one of the API quick start, and here you will have a single Docker run to create the Stargate node in developer mode. And now this container will act both at the Stargate node and Cassandra, so holding your data. That's just a convenient way to run some tests. So this is what I will do. And I do have it running right now. So if I keep moving, here you can see that I do have some Docker Stargate started. I also have CQLSH as a Docker container. I don't know if you are aware, but the Nuvo provides some Stargate, not only Stargate, but CQLSH Docker node, and I just bring back this command. So hey, this is what it looked like, and with that you will have a CQLSH running, and this is what I do have as well here. This is my CQLSH. So if I go back here, so I do have running the Stargate, and I can access the API on localhost, and I also have my CQLSH over here. So I can here describe the key spaces for you and see that as of now, I do have the system key space and a key space here called Java. And with that, I'm all set. I do have the Stargate node running, and I do have a CQLSH to see what's happening in Cassandra. So going to step 3, use SQL API. Let's see what we can do, right? So first, what we need to do is to create a key space, KS1. So here I will go in my SQLSH console, copy that. Oh, you know what? I was too fast. I told you it's a single node. So what I would like to do is really to put my replication factor to 1. And here I'm good to go. So I will then use my key space. Okay, and I will create two tables. So one table and one user-defined type. So video, and here video format as a user-defined type. Okay, so nothing new here. Really, the default way to use Cassandra. And if I describe my key space, you will see my object ready to go. Okay, so here I do have a user-defined time and a table. So then I can populate some data. So here, just copy pasting. You can insert some JSON in Cassandra. It's not a well-known feature, to be honest, but you should use it more. Except it will enter your table only if you match the target schema. Otherwise, so it's JSON oriented, but here you do have a schema. You need to match a schema. So you can retrieve the videos, like, of course, select star, but you can also retrieve the one single video, because here, if I recall, video ID is both my primary key and full partition key. I can also select JSON from video just to retrieve items as a JSON. But here, nothing really new to show to you. Now, start the magic. So this is my Swagger, and I would like to use the data API, because data and schema are the REST part. And if you see here, we do have V1 and V2. I would like to use V2. It's the most up-to-date, and this is, as you can see, where we do have most of the endpoint now. So let's see what we can do. So step 4, use the REST API, and we need to get a token. So with this curl command, so let me go here, enter that curl command, and as an output, I get a token over here, a token that will be available across all Stargate API for 30 minutes by default. Okay, so let's copy that guy and move to the Swagger UI. So first, what I can do here is list the key space. So V2 schema key space. So how Swagger works, it's the first time we are doing that. You just press try out, provide your token, execute, and here you see the result. So we do have here system distributed, system, Java, and we do have here KS1, the one that we just created together. Here I do have a data center because I created the key space with the network topology. If you use simple strategy for your replication strategy when you create a key space, you will get only the name. Okay, so it seems like the API is working. So what can we do? We can list the table. So get all table, try out, providing KS1 as my key space. Here I do the video table we create together. I can also retrieve the user-defined type. So here, if I go to now types, try out, and provide the same key space, we should find our UDT, which is video format over here. Okay, so far so good, but it's not only retrieving stuff from the schema. You can also create some tables. So here I do the create table, try it out on the key space KS1, and here look at what the JSON look like. You need a table name, define the primary key, providing partition key, clustering key, and the rest of the column definition and the table option. So here I will define a table user, first name, last name, email, color, first name, partition key, last name, clustering colon, and the last name, clustering colon ordering will be ask. So copy here, pasting here, and executing that. So let's see. So 201 HTTP code for created. If now I go to list the table and re-execute that again, I do have my video, but also I do have my users table over here. Okay, so far so good. So now if I want to insert some rows in my table, doing the full create, read, update, delete circle. So I will move from schema to data, DML. So we created some table. Let's put some stuff in there. So locate V2, so post key space table name here. So try it out, provide my token, provide my key space name, my table name, it's users. And here, this is how we enter values. So we put some key value, totally generic. And with that, we will be able to enter some value. So here, the full primary key is returned, Cedric Lunven here, and I can add a second one and third one. yeah, you know, nothing special here, but it's cool to see here that you can enter stuff. Oh, I still have here my SQL SH. I can select anything from the table we just created, which is now users. See, so it's not it's not it's not a recorded video or something. We are really working with Cassandra. So I had multiple read multiple rows. So now if we just want to retrieve the rows, I can try it out. Okay, I need my token again. So let me copy my token here, retrieve the rows, key space name, table name. I think it was users, the fields. That's pretty cool. Here I do have everything, but let's say I only would like to retrieve, I don't know, first name. I can just say, hey, well, I would like to retrieve just the first name. So let's see how it goes. And here at the output, you see only the first name has been retrieved. So it's kind of what GraphQL can do, limited the payload output, just providing exactly what you need. And that's pretty cool for REST. I can delete a row, same. So here I will go here, try it out here. So this is, oh, I always need to copy my token from call to call here, and I will delete my row, key space guys 1, table users, primary key. So here I will use my here, and here I provide the partition key to do delete at the partition level. So you can delete multiple rows in the single call. This is why here we do have a S at rows. Okay, so far so good. So keep moving. We can also search a table, and it will be my, I think, my last API invocation for the rest. So go to search a table, try it out, provide a token that I keep copying from one code to another. Here it is. Get the key space. So it's still KS1, table name, no change, users. And here I can provide a where clause. And the where clause will be in JSON format like that, where first name equals David, and we can say, hey, maybe I would like something more. So I just say comma, and here I add a second filter if I want to. And so I just execute that, and I have nobody called David in my database. I think it was Kirsten, right? And here I do have Kirsten retrieved. Okay. The requests are paged in the same way as the query are paged in SQL only, using, you know, by default it's 5,000 for the page stays. In HTTP, because it's quite verbose, the default page size is about, it's 20. And you can provide here the page size when you search for a table. Here it is, page size. Okay, so that was the REST API, really, really close to what you can do in SQL. So here we delete Cedric, only Kirsten remain. So that's cool, but we do have way better for you. So second API that I do have for you is the document API. So I showed you just before that you can indeed run some JSON insert and retrieve with Cassandra, but you need a schema validation, and nested object is pretty dangerous because you will need to create some tombstone, especially if, I mean, because the nested type needs to be frozen. So what can we do? Well, what we'd want to do is to be schemaless, or to be more accurate, validationless. because you want to insert JSON. A JSON document does have a schema. You know, you cannot put anything in JSON. You still have that curly bracket and double quote field name, semicolon, double quote value. So you still have a format for a JSON object, but there is no real validation. So we would like to insert those JSON no rule in Cassandra. So how can you do that? Well, we will use something called the document API. The idea is really to insert and retrieve any JSON and do not care anymore about the schema, but it's more advanced than just saving some text on a column in Cassandra. What we do is we are using something called the document threading. So for now, instead of talking about a table, we are talking about collection. And each time you create a collection through the API, a technical table will be created. Always the same schema, always the same column names, and you will have here a key, which is the document ID, multiple PO to PN, having multiple levels in your JSON, and at the end, the terminal value, the leaf. So let's see what it looks like. So if I give you this JSON ABC, first level AC, second level B1. So 2 rows in Cassandra. So X is my document ID. PO is the first level, so A. Do we have a second level? Yes, we do. It's B. Do we have a third level? No. So P2 will be empty. Everything will be empty up to here. It's a double value, so I will fill double value. If it would be a string, it will be text value. But hey, that's really how it works under the hood for Cassandra experts. The REST API will do the abstraction for you. You don't have to know all these internals to use the API, but still that's cool to know how it works. For the second row, C, each does the first level. So here I do have POC and P1 is null, and I do have terminal value 2. I could do the same with a list. So now C contain not just the value 2, but a list containing object D2. So now the second row is, so first row is the same, second row C. So now P1, hey, we don't have a name, so it will be a list. So the trick here is to provide the index of the list, so square bracket index square bracket, and get the nested object. So here I do have D, which is the attribute name, and 2, which is the value. Yeah, it's working like that. And with that, let's go back to the demo board and doing a little bit of document magic. So I will get back my token. So I think we use it for search the last time. My token is still valid for 30 minutes. So now I will move to the document part. So what I would like to do is say, hey, so first I can list the namespace, and don't be surprised the namespaces are exactly the same as a key space, but for someone working with document API and database like Mongo, they like to talk about namespace to collection document. So in the document API, we are reusing the same attributes. So here I can create a document. So let's create a document. So let's see, create a collection. So let's see, create a document. It should be green because we create something. So create a document. Here we go. So try it out. Provide here namespace ID. Well, I would like to reuse the same namespace or key space that we use until now, case 1. Collection ID. Hey, I can put whatever I like. If the collection ID does not exist, it will be created when I ask to insert a document. So I can here use col1 for collection 1, and here this is my JSON providing here a video, see, with nested item format frame here. So execute that, and as an output, it's if everything okay, I will get a token ID. Okay, so not a token ID, but an ID. So that is my document ID. Okay, so what we can do first is retrieve this guy. You know, like get document by ID. So search document in a collection, get a document over here. So try it out. Here I will provide the document ID immediately. I will also find my authentication token. Namespace ID, no change. Collection ID, I put col1, and here you can retrieve your document by ID 404. So do I? Oh, I see. I let my quote at the end, and here I got my document. Okay, so we did the read. We can retrieve the document by searching. So not sure that I would like to execute it, but if you search for documents, search documents in the collections, here you will provide, as usual, a token, namespace, collection ID, and the where clause. So the where clause will be the same as the where clause that I show you for the rest. So stem structures like where clause, where equals, blah blah blah, something like that. Okay. And you execute, you get the item retrieve. You know what? Let's do it. So what I did retrieve a document. So what I do have get a document, get, hey, here it is. Okay, just to be able to copy paste the attributes. So this is my token ID. Okay, namespace, this one again, collection ID. Hey, here we go. And where clause, here we go. So let's see if we can retrieve our guy. So the where clause is working. And as before, here you do have fields to retrieve. And maybe I only want, I don't know, my frames. So I only want the frames back. But request, so hey, field name. So maybe now he needs some stuff like that. See, not sure why field names. Oh, is it frame valid? Let's go back with my object. Yeah, probably that's just me. Frames. Yeah, not sure. Do you like emails better, or do you need some quote? Okay, fields must be an array of JSON emails, blah blah blah. Okay, so you want something like that? Hey, here we go. And you want an array, so what we would like was frames. Are you happy with frames? Hey, here we go. So as you can see, here I do have the list of fields provided as an array. Okay, so we created a doc, we retrieve a doc, we search for docs, delete would work exactly the same, and which is cool. Cool. So if we describe now the tables, we do have a new tables called col1. But if I select anything from this col1, you will see that it's pretty. Do I use? Yeah. Okay. You will see that it's pretty scarce. So we do have P0 up to P63 here. Yeah, so 64-bit. And here you see all the, so P key is your document ID, PO is my email, everything is empty up to my leaf stuff, as I told you before. Okay, it was the document API. Finally, we would like to show you the GraphQL. So GraphQL, really, it's it's not so new. It's almost 10 years, but it's really changed or became more visible when it was announced in 2016 that GitHub will be using GraphQL moving forward. It's pretty interesting because you can have a single endpoint and multiple ways to consume the endpoint. So it's a way to implement API and prioritize giving customer precisely exactly what they need. So you describe your data with entities, you import your schema, and then when you create a query, you exactly provide what you need. Same as the endpoint I show you before, just list exactly what you need and get predictable results. Okay, so in Stargate, until now, I've shown you the SQL endpoint, the REST endpoint with Swagger. Let's move to GraphQL endpoint. GraphQL tool you do have multiple GraphQL tool. One is the Playground, one is GraphQL. Inside Stargate, Playground is provided. So let's see what we can do. We can mine nice stuff. So here I'm moving to a GraphQL. I will move to the Playground. So here it is. Guess what? No new. I need a token. So can I steal the token somewhere? So here would be good. So first I need a token. So let's put my token as a header and execute that. So we invoke the endpoint on the schema, so DDL, so GraphQL schema, and I use a first query just to list the key space. What is neat with GraphQL is you do have the list of everything available here on the right side. So I'm able to list the key space, the table inside the key space. So anything read-only is queries, and anything to edit the data are mutations. So nothing new for you working with Cassandra. It's also called mutations. Okay, so let's see what we can do. We open the GraphQL Playground. And so what we want to do in the key space, let's say create a table. So in the key space KS1, let's create the table books and the table author. Okay, so this is how we create those. In Playground, you do have the completion, so you know what parameter to provide. And if you look at the schema, so here we have the schema, table names, partition key values, pretty close to what we had in REST API, right? Let's try to create my tables over here. So it seems happy. Can I have my sanity check? Describe tables. Here we go. We do have books and authors. Okay, that's good. Okay, this is my token. Let's switch to the data. So to go to the data, I switch tab. I'm now using the GraphQL tab. Different tab is different process on Playground. I need to provide again my token. And here I would like to work with the key space KS1, the one we keep working until now. And I will populate my table, providing a so-called mutation. And here we go. So in the key space KS1, I will work with my books table. So because I design two tables, now look at that. I do have authors, books to work with for books. I do have this query to work with books. This is exactly what I will do after this one. And I also have insert video, insert user, insert books. Speaking of which, it seems like insert books does not have these capital letter for B, and it should work better like that. And here I do have two books in my table books, sanity check from books. Here they are, okay? but I can also retrieve them using a query, and here it is. Here is my query. So query on book, providing the title, and if I only want the title, I do that. And if I want more than the title, and that's exactly what you want to do with GraphQL. If you also want the author, just ask for the author. And here we go. It will be based on exactly what you need. Okay. Everything I just did was on local Stargate. You can also work with Astra. It's free to use, up to 80 gigabytes and 40 million queries a month. So in the instruction, here you have some comment how to do so. But I won't do it in front of you. I will keep moving with the presentation. Okay. Okay, this is my slide over here. Okay, so we did a demo of the 3 big APIs. So what's next? What can we talk more about it? Well, if you look at the endpoints, that's quite some work, right? So many things are there, so many endpoints to learn. And if you want to build your app on top of the API, maybe you don't want to implement all the REST calls. I know it's fun, but maybe if we could provide you something better, that will be welcome. Well, my team is leading the SDK building. So we do have 3 SDKs for you: Java, JavaScript, Python. If you remember my bio in the first slide, you know I'm a totally Java guy. So I will talk on the Java one now, but everything that I show or do would be the same with JavaScript and Python. Okay. So you have multiple libraries. You have the Stargate SDK to only interact with Stargate, and this is the one I will show you in a minute. But I also told you about Astra, which is Cassandra plus Stargate plus Pulsar in the cloud as a software as a service for free. And here you do have the Stargate SDK leveraging the Astra SDK leveraging Stargate SDK. And even to build some Spring application for the Java one at least, there is a Spring Boot starter. So just import the starter, enter a couple of keys, and you're good to go. All the SQL session will be provided to you. So I think I do have time for a little bit of free fall stuff like everybody love at conference. Live coding. Okay, so here I do have a project, and I mean it's the Stargate SDK itself, but it's just a project where we imported the Stargate SDK. So we will do first method, and what we will do is it's a test. Okay, let's have fun. Blah blah blah. Import what I need. Okay. So I need to work with Stargate. So Stargate is auto-closable. So I would say I would like a Stargate client. I will call it SC Stargate client.builder.build. Okay, I will open that. Okay, so now I start thinking. Builder. Okay, so I need to provide stuff. We know that Stargate is running locally. So with credentials, we have used Cassandra to connect until now. Okay, that's it. I think we also need a contact points. Let's say, I mean, it's not even mandatory. We are working locally, so localhost. Okay. And we want to enable Stargate. So we will say with API node. So we have a single data center. So Stargate client will do the load balancing failover if you do have multiple nodes. I told you about the client side load balancing, but the server load balancing. But here the library also do client load balancing. Okay, so here I need a Stargate node config, and I use all the defaults, so I can simply say localhost, or just say, hey, both will work. And with that, if everything is okay, I should be happy. So let's see what you can do. With Stargate API, it's a fluent Stargate client. It's a fluent API, so I can. Let's use the REST API, for instance, and let's list the key space. So here I do have this stream of key space name. So what I will simply do is just system.out println, right? So if everything is okay, I can run that guy and I will see the key space names in the console. So run as unit test. And here we are. So woo, live coding, no demo effect. So because I provided a contact point, I do have the SQL session enabled. And because I provide a HTTP endpoint, I do have all the three guys open. I provide a data center name, so the data center name is used in the SQL session. But if I drop that, the library use some default, but it should tell you that, hey, man, you should provide stuff. Okay, so here it is, no contact point provided using default, no data center provided using default data center 1. So yeah, now the guy is pretty intelligent and will do it for you. What can we do? And then I will just show you a last slide. Okay, what we can do? I don't know. Let's try to work with SQL. Okay, so SQL session.get, we know it's working, .execute. So what do we want to execute? Select, let me see, data center from local, from system.local, okay. .1, we know on local there is a single one, .get string, okay. So we want the data center value. Okay, and because I'm lazy, I will probably just output that in my console, sysout. Okay, here we go. Yeah, okay, let's run that. Do we have the data center? I don't like the warning, so I will put that. Hey, hear that? It's working. Yeah, that's the collection. No, I think we're good. Hey, maybe let's display a document and then we will be done. Okay, so sc.api document, the namespace. So I think the namespace we created was ks1. Okay, dot collection. So which collection did we create it together? I think it was col1, right? We did col1, okay, and say I don't know. I don't know. Find all, yeah, but I would need some object to retrieve them. Let's see what can do. Yeah, I need a doc. Oh, so I will just retrieve the collection definition. Okay, let's do that. Collection definition, coldef equals, and I think it should be optional because we don't know if the guy is there. Okay, and so what we want to do is see if is empty. Okay, I don't need that anymore. And if is empty, and I hope it is, what can we show you? Then to retrieve some data, I need an object that match that structure. Blah blah blah. Called def.get dot I don't know, get name. Okay, let's do that. Here, all that to just display col1, but you know, never mind. Just for you to grasp how to use it. Just say the API you need, the namespace you need, the collection you need, and here. So yeah, the collection one exists, and his name is collection one. Then with that guy, I can find but it will give me back some object. Oh, I think I can use string. So okay, so yeah, I'm running out of time. Okay, so stream the document. But you know, when you like coding, and here I would like to do find all. And Guy, I would like you to give me just string. Give me the JSON. I don't care about marshalling. Okay. So what do we have here? Is it happy with that? Okay, seems he is. Okay, so and now what we want to do is say, hey, call like we do here. Okay. So we don't need the output, we just want to do that. Okay. So hopefully, never tried that before. So document namespace collection, find all as string. I don't need any. Class, and this is something we should provide in the SDK. To be honest, not to have to provide stuff. So let's see. Is it happy? No, it's not happy. It cannot marshal the stream itself. So I need really to provide an object and not a string. But hey, so I public class video, and I think we use something called like, and I will be done. Okay, so blah 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 video ID, video ID. Okay, are you happy with that? Hopefully it won't ask for everything. So public string blah blah blah, source generate getters and setters. Okay, default constructor. Okay, all right, and it's a public static class. Okay, so now what about now? Are you happy with that? Public static class video blah blah blah. Okay, and now if I want to retrieve not strings but video, are you happy? And will be my last try because I still have one slide. Hey, we do have a document. So yes, so for each we know that we do have a document. So let's show the document ID. So dot map document. Come on, Cedric, stop playing. Yeah, anyway, the video is here, has been retrieved as a document. Okay, so we also provide at DataStax a way to deploy both Cassandra and Stargate in Kubernetes environments. By the way, this is exactly what we do have in Astra, and it's a way to expose Stargate at external. And with that, I think I cover it all. Next week, we will have gRPC, and the demo will take even more time. But until now, hope you enjoy it. This is my coordinates. If you want to join my network, would be happy to have you. And thank you for your attention. And I will be with the others in the Ask Me Anything question if you do have questions, because I think I've used all my time. Thank you very much.
And hello, everyone. Here we are, ready for the application development workshop. So we've been announcing that in the other room, the workshop room, that due to technical glitches, we had to swap. So if you are in for the certification talk, I advise you to please join the workshop room, because here now we are speaking about application development. So without further ado, I will start. Okay, so application development. I think by now you know much about Cassandra. You know what kind of database it is. You know how you have to approach modeling the data for your application. Now it's time to speak of what happens when you want to actually write your application. You have an application that you're about to create, and you need a layer for this application to communicate to the database, right? So you need a layer between your actual app logic and the database storage, Cassandra. Usually, what is the answer? The answer is you need a driver. Whether you have an API or you have say, a serverless function because of your architecture choice. Anyway, you need drivers to access the database. Well, that's the standard answer. I'll mention that there is a different answer, at least Cassandra offers a different answer called Stargate, which is something Cedric has described extensively in a previous talk in this room. It is basically an API data layer that makes it possible to access the data in Cassandra or Astra DB for that matter, by means of simple HTTP request by using different paradigms. So you can look at your data as a document API, a GraphQL protocol, whatever. And that's very cool because it makes it possible to just use HTTP request from inside your application or your API. Today, however, we will stay on the classic route and we will speak about drivers. So that's also because Stargate was already described. So let's go back to drivers. There are drivers for Cassandra for the most popular languages. You see C, C++, C#, Ruby, you name it, Node, Python, Java. And they more or less all offer the same set of advanced functionalities, as you can see here. Many of them we will see more in detail later, so I'll just mention that today we are going to focus on the Node.js drivers. That's not particularly a limitation of this talk, because most of the features you'll see will have their equivalent in the other in the drivers for the other languages. So we will just stick to Node. Okay, so this talk we have 1 hour, and well, we have 45 minutes now, so even. So there will be, unfortunately, no time to have a real hands-on with you, but I will provide you, and I'm doing that in this slide, I will provide you with all necessary information to go there and do the practice yourself. Today, I will just show you a little demo. Now, the drivers for Node, well, you find the documentation at this address here, and I also give you here the address of a repository containing all the practice code, all the code that is used for the practice that I'm showing, the demo that I'm showing now. But this repo contains much more. Now let me, okay, so you see this GitHub, Emidactylus, etc. This is my GitHub, and let me show you very briefly. This is the repository, and it is not just a bunch of lines of code, but it has an actual README that makes this repo a self-service, say, exercise room. So you can start reading, and there are all instructions to set up your testing environment, starting from creating your database if you want to use Astra DB or using Cassandra. That's, say, using a standard default Cassandra installation. That's your choice. So this repository guides you through setting up your environment in terms of dependencies, creating the database, connecting to it, creating you will need a database, a key space, connection, so parameters to connect, whether you are using AstraDB or Cassandra. You see there are all details. So in order to start running some sample code, which I will do momentarily, you also have to load some data in your database, and it is all explained here. By the way, there was a question in the Ask Me Anything session about how to load CSV into AstraDB. And we answered, yes, you can. By the way, this repository in the instructions tells you also how to do that, for a simple reason that in order to test the code, we need a table, and I will quickly show you how what is in this table, in this test table, to just run some reading code. So creating the table, populating the table with some data. Okay, at this point you have your if you do this practice by yourself, at this point you will have your database, your data, everything ready to just run the code. Luckily, I already did that for you. So I have already my database called Node Practice, and if you go looking at it, I will keep the SQL console ready to double check what happens with the driver code. You will see desk key spaces. Desk key spaces. You will see that there is a key space called chemistry. That's the testing key space. So if I use that, you will notice that there is a single table here called elements. And if you select from elements a bunch of lines, you will see that there are chemical elements. So symbol, atomic mass, atomic number, name, and partition key is symbol. It is just a table with 100 or so rows for testing. Okay, so back to the repository. This is the situation we start from. And now let me go back to the slides. Back to drivers. So we are in Node.js and we want to connect to Cassandra or to AstraDB for that matter. First, how do you install the drivers? Well, that's a standard npm install or in terms of a package JSON file. This is what you probably want to use in dependencies. Nothing particularly strange, right? And let's go on. So how do your drivers connect to the cluster when you start using them in your code? Well, let me say that the drivers are pretty clever because you know that Cassandra is cluster, a ring. But luckily, when you instantiate your driver from your application side or your API side, you will just need to provide 1, 2, maybe possibly 3 at least contact points, which means just the IP address of a few of the nodes. But actually, you can also do with 1, unless that one is down. The point is that you give the drivers just the contact points, which are the purple nodes in this sketch. And then what happens? The driver speaks with these contact points and asks, hey, tell me the topology of your whole cluster. Luckily, these purple nodes, as any other, are constantly gossiping to each other, and they are all updated to the current status of the whole cluster. So the purple node answers back to the driver and tells, hey, this is the topology. Now, from that point on, the driver knows the whole topology and is able to speak to the whole cluster for any query that will come. That opens the way, and indeed drivers implement that. That opens the way to load balancing and other clever things, such as going straight to the right node when you specify a partition key, for example, which is something that all Cassandra drivers are able to do. Okay, so let's look at some code. Most of this presentation will show code with some commentary. By the way, something that is very important is that in the repository, you also find these slides. So you can go there and download the slide deck and look at it at your leisure. So, okay, so how do you connect to Cassandra? Well, you import this dependency, so Cassandra driver, and then you instantiate a client object, passing a config object. In particular, one of the parameters is this contact point. As I said, it's a list of IP addresses. Then you call client connect. you do whatever you have to do, and then for cleanup of resources, you should always do client shutdown. That's it. So that's how you create a client and keep the connection. Okay, the client should be a singleton, so one single instance should be shared throughout the whole process. Now, a detail, if you, instead of using the standard Cassandra, you want to use AstraDB, good. The only difference is the config object that you pass to the client when you instantiate. So instead of giving the IP and possibly credentials, you will give this particular kind of objects. And by the way, the Astra, the Astra UI will tell you exactly what to do. So you need a secure connect bundle, which is the location of a zip file that you previously downloaded containing basically a bunch of certificates and similar connection information. And then you will have also a client ID and a client secret that will make your connection authenticated. Okay, so as is best practice in this case, obviously these variables are to be treated as secrets, so they are in some environment variable, probably out of your repo or whatever. And so here in the code, I'm reading them from the process, from the environment variables. Okay, so let's look at the first full example. So by the way, on screen on the slides, I will pretend I'm speaking to standard Cassandra installation. So you will see here IP addresses, while the code that I'm running will be exactly the same, except I will use AstraDB config. So I will contact the Astra instance that you just saw here, the one with my chemical elements. So what does this snippet of code do? It will connect to my client, and then in the main function, I open the connection, I run a query, I take the result, and iterating over the result, I just print them. Now, something is already clear. In this case, when I want to run a query, a SQL query, it is just a string that I will pass as argument to the method execute. So client.execute query, then something. So this execute method in this way will return a promise. I will then act in the then part of the promise, and the promise will, so the callback in the promise will have a result, and this result is an object with a rows, and a rows is something I can iterate. Every item in the row will have name, symbol, etc. And those are exactly the name of the columns. So if everything works, I have here a node, I have here a shell ready to use. If I'm not mistaken, I already sourced the environment variables with the connection parameters. I already npm installed everything, so I should be able to just run node code, and this is exactly what you find in the repository, the sample snippets of code. Connect, connection Astra. So let's see what happens if I run this code. This is exactly what you saw in the slide. Aha, look, I'm reading all the chemical elements and I'm printing one by one name and symbol. You see, all of them. At the end, I will close the connection, and this happens here after the iteration over the rows. So this is a way to, this is a very simple case where I just open the connection, do a query, read the results, and act iteratively over every row in the results. Cool. Let me just mention that the client connection can be configured in various ways. For example, here I am explicitly specifying a load balancing policy that, as I mentioned earlier, is token aware, so it will try to go for the correct node holding the data for that partition I'm asking. So this happens on the driver level. So I will directly contact the right node once I know the whole topology. Once the driver knows the whole topology of the cluster, it will be able to just go straight to the node containing my data. I also set an explicit reconnection policy, a retry policy. So there is quite an amount of configurability in how the client is instantiated. Okay, so let's have a closer look at how you query the data. Okay, so something that you already saw is that to run a query, basically you take a SQL statement as a string and you give it as argument to client execute command. Now, you have noticed already that there are a few awaits here and there, and I also mentioned that client execute returns a promise. Well, that's not entirely true, but one of the ways to use it, yes, it is promise-based. Alternatively, the same command can be invoked to give in a callback fashion. So let me just run this very small snippet of code. As you see, there is a string that contains a whole SQL statement that creates a new table. So this new table is called metals, and it has columns that are kind, name, density. So this is a specialized table to hold information about metals. How do you run this command? You just client.execute creation command. So let me run this. To do that, I will open interactive REPL to Node, just because I want to recycle this connection while I run example after example. So this is exactly the creation command you saw in the slide. So there is a whole string that is create table, etc. And I use client execute. So let me just run this thing. Creating a table is a schema operation, so it's a DDL operation, and it takes some time, very much more than inserting data or treating data, but it has executed. And let's see desk tables, because I have my SQL console here in Astra UI, and sure enough, my metals table is there. So desk table metals, let's see. And there we go. This is exactly the table we just created in Node using the drivers. Nice, huh? Okay, so how you write data? Well, the baseline case is a long string with the very same thing you would type into SQL, as I do here. So client execute, insert, blah, 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 blah. Well, this I can run for sure, and I will do that. That's exactly the same. I just client execute a long string. It has run. Let's see, select splat from where I was inserting in metals. So let me read what is in metals. Okay, I inserted copper. Copper is a regular metal and it has a density. Well, let me tell you, copper has a much higher density. This is a mistake, but okay, I pretend copper is very lightweight. Okay, so that's a way, but that's absolutely far from being the right way, because I'm just writing everything into a long string, and that's I might have trouble with escaping quotes. That's not efficient when it comes to serializing numbers, and it is also in general prone to injection attacks. As you know, let's say I'm writing an API, I certainly don't want user-defined, user-provided input to end up in such a statement, right? Injections and all that kind of risk. So I can do much better. I can do much better means I can separate logically the statement, or better, the blueprint for a statement from the actual values. So you see, client execute, then first argument is insert statement with placeholders for the values. And then I put the values in an array that is matching these question marks. But you see, in this case, I need a third argument, which is type hints. That's because Cassandra has a very rich type system. It has text floats, which are not the same as integers, and so on. And JavaScript is not does not match that type system. So in order to make sure types are properly treated in Cassandra, I have to explicitly provide type hints. So I'm telling that the first argument is a text, the second is a text, and the third is a float. as opposed to a double, for example. Let me run this statement. This is another insertion where I insert the metal palladium, and there we go. Let me do my check, and sure enough, palladium ends up in the table. Now, let's do an experiment. Let me comment out the type hint and run this insertion again. Uh-oh, something went wrong. And if you look at this message, it really smells like a type mismatch kind of thing connected with serializing, indeed. Okay, but I can do even better, because probably if I'm doing insertion over insertion, I'm running statement after statement, I'm probably not in the mood of providing type hints all the time. It's really cumbersome, right? So I can use prepared statements. What does it mean? Well, I have my statement. Look at this first definition. I have a string that is my blueprint for an insertion, and I call client execute, blueprint, arguments, and then I pass a third option object that is prepare true. So what does prepare mean? Well, it means, dear driver, speak with the Cassandra machines, with the Cassandra nodes, and ask them to kindly prepare their knowledge over types and get this statement ready for the next times I will. So the first time, the nodes will get knowledge on the types connected to the fields that I'm writing. Then every next time the statement is run again, I will just have to pass the data, and the serialization with knowledge of the types will be automatic. And indeed, as you see, I can promise you that in the next block of code where I insert Mercury, this prepare true again, this second statement will not trigger again a lookup in the schema. It will just plain simply pass the data, and they will be serialized the right way, because I already had the node prepare knowledge of the types. And see, there are no type hints anymore. By the way, these two examples also show that the second argument can be passed either as an array or as a name, as an object with names matching the column names. So you see, here I have an array, zinc, but for Mercury, I'm passing an object that basically reflects the shape of the table and the column names. Let me run this part as usual. So I have my prepare statement, which is just the string. Then I execute insertion of zinc. Now, trust me that there has been some special communication between the driver and the nodes. And the nodes now are primed to later accept fast serialization of new insertion data without the need to look up again the types. And there are no type hints anymore. Now, another small look at the table, and sure enough, Mercury and zinc have arrived properly. Yeah. Okay. Now, something more on writes. I mentioned promises. Indeed, if you call execute, client execute with this 3-argument syntax, the first is the statement of insertion, then there is the array or the object with the values. The third might be this option set, prepare true usually, and this is a promise. Then I can have my then statement and my catch statement as usual. So in this case, I'm inserting, well, somebody hijacked my database, and I wanted to use them for metals, but somebody wants to use that for metal bands. So they are inserting AC/DC, which is not a regular metal, but it's a band, okay. But still, this client execute will probably succeed, in which case I will see this console log AC/DC inserted, executed. So let's check this. Insertion of AC/DC, and that's exactly the code that. Now, here I prepared a long text file with all snippets of code that I wanted to show you. In the repo, you will find them every one of them as standalone code. So just everyone will be just run with the usual as a script in itself. So don't worry. Oh, it worked. You see, I have my nice console log, so everything worked. Cool. Alternatively to the promise API, I can use a callback-based API, and that's very simple because the same client execute statement will just have a fourth argument, which is a callback, a 2-argument callback. So either error or result will be non-null. So if I have no error, the insertion worked. If I have an error, I will have to print whatever it is. So you see now I'm inserting another metal band, Iron Maiden, and I expect this statement to succeed. So I probably will see Iron Maiden inserted. Let's see, Iron Maiden. And if I run the snippet, yes, Iron Maiden inserted. Let's have a quick look at the metal table. And there we go, AC/DC, Iron Maiden with type band. Very good. Okay. Now, let's speak about reading. How do you read data from the database? Well, again, nothing so much different. I use client execute. I just have a different query, a select instead of an insert, probably. And even here, I can use the placeholder syntax and provide the value separately. So now I am reading every metal of kind band. So I will probably just see my 2 metal bands. So you see, I'm just reading, and now the callback associated to the promise will look at result.rows, which is a list. I can iterate on it, and now in this case, I just print some 1 line for every band that I'm reading. So here I'm reading name and density for the metal band. Let me run this small snippet. So it's a promise-based way of reading, and let me make a bit of room. There we go. So here, everything worked. And that's how you read. That's one of the ways you can read, because in the same spirit, you can also use the callback way of things. As you saw ready for writing, execute now will have a 4th argument, which is a function of 2 arguments in itself, and the second is the result. Now, for some reason, I want just to read the copper, the 1 line, the 1 row of copper. So I'm reading from metals where kind equal something and name equals something. In particular, regular metal copper is the name. So I can just read rest.first, which will be a single row. And this row will have density because I selected density, you see in the blueprint of the query. So let me just show this at work. And there we go, copper density. By the way, I reiterate that copper is very much heavier. Okay. Okay, so reading, there are various other ways of reading. One is this each row method. So each row basically contains iteration over all rows matching my select. Each row returned by this select will be subject to the 4th argument. So each row has 5 arguments. The 4th one is a callback to be run on each individual returned row. And the 5th will be called in case of errors or with a null argument when just when I exhaust the number of the rows. So when every row has been returned, then at the end, this 5th argument, which is a callback, will be called with argument null. This is when here. So in the console log finished reading, usually I might want to be clean up, so shutting down the client. So as you see, this query will just look at all regular metals, printing name and symbol of the density. Sorry, name and density of the metal. Let's run this small piece of code. And this is just a showcase of the each row method. And there we go, including the callback for when the query exhausted all of its results. Okay, this is just a quick tour. Let me just mention that you can also run batches. So you can run batches very easily. You can you just have to wrap every statement making the batch in an array, and then you have this nice method client.batch. That's it. The rest works like usual. So either promise or callbacks and etc. etc. I will skip that to make sure to finish on time. There's nothing particular unexpected there. Okay, so before going on, I'll mention that the issue of execution profiles, that's very useful because consider a real life application will probably need to support different workloads at once. So you might have a single application that needs a different consistency level here, a different timeout there. It needs to work on a specific data center there, all on a single driver, on a single connection. How do you do that? Well, you can, when you instantiate the client, as you see here, I am passing in the options profiles object. So an object with profiles, which is a list of profiles, which are instantiated here. And each one of them might override some features, some settings such as timeout, consistency levels, and so on. And this just makes the client ready to use one or the other of the profiles. Now the client is ready, is primed to do that. And when I run queries, you see I have a select that. So I have two different select here, three actually. And if I pass in the options which execution profile to use, I will. This query will be run with one or the other of the settings. So this is how you achieve mixed workload in your Node application. And again, this is not much different from what happens in Java, in Java or in Python. The concepts are very much the same. There's much more that you can configure. So you can pass many other options to each row method, to execute method, and so on. You can directly set the consistency level, as you see here. You can define the fetch size, more on that later. You can redefine the timeout for that one query execution, policies, and so on. Okay. Now I want to show you very quickly a mini API, a full-fledged mini API. You remember the table with metals? Let me show that to you again. I had my tables here, my metals here, and they come into ways, into types. So there are regular metals, which are actual metals as in the chemistry sense. And then there is this intruders. Somebody is making fun of my chemistry. For some reason, my customer works in metallurgy, and they want an API to make it possible to, create and read actual metal properties from this table. And there we go. This is a full API written in Express, very simple, that showcases how you can use Cassandra drivers within typical JavaScript API. So you see there is the usual Express stuff. There are a few endpoints in the root. Inside the code associated to the three roots, I use my client. So the client is as a good singleton is instantiated here in the outside before the three endpoints. And then for every endpoint, I just use the client, execute stuff, and maybe return stuff. That's very simple. The code is there in the repo. What happens? Let's look. So obviously, you can do any kind of usage of the Express properties in your query. So for example, in the get metal by name, that will give me back one single metal and its properties. I'm using the rec params name as part of the query, for example. Or in the post to create a new metal, I will use the rec body, adding something maybe for an insertion of a new metal. So it so happens that I have this API ready to run. So let me close the interactive REPL and let's see node code API.js. So now the API is there, ready, running. Let me open another console. And I will just run a bit of curls. So, okay, maybe this. So the API is ready for me on port 5000. You see, with this first curl, I'm just getting back all metals of the regular kind, as you see here in the queries. So let me run this curl. You will probably see a bunch of metals nicely formatted as JSON. Or I can look for a single metal with a curl with this get. Sorry, I did something very stupid, I think. I didn't insert silver because that was inserted in the batch. So I have to run. Okay, I can change the metal to another one. Let's say copper. There we go. So I have my nice metal back. So everything seems to work. And now I will insert a new metal called harmonium, which, by the way, does not exist for real, but I'm having fun of chemistry. Inserted through is the response. So I think harmonium with its funny density has been inserted to my database. And let's check. And there we go. So this API is indeed working. That's a very simple example, but still. Okay. Now, I want to show you a few things about pagination, because that's most often a very important thing. Now, when your driver queries, so when you query to get data, when you do select, as we did so far, usually you get at most a number of items, a number of rows back. That is your page size, your fetch size, and that by default goes to 5,000. So a lot of rows. And if you are a good developer and you obey the best practice, then you are reading from a single partition. So you're reading a lot of rows from one single partition. If you don't do any kind of pagination, and for some reason your partition has even more rows, then you will get just 5,000. Then maybe you want to redefine fetch size to 5 or to 2, and you will get just 2 rows. But you might want, and the driver is able to handle for you, you might want to handle pagination automatically. So you want to get rows 2 at a time, but you want to get all of them. So 2, then other 2, other 2, other 2. And from outside, from your code, you don't want to take care necessarily of all of the intricacies of page state and all that. To do that, you can use the asynchronous iterator, and you just run your select with this syntax for await const row of results. And this body will be executed for every row, and you will not even notice that behind the scenes, the drivers and the node and the Cassandra cluster will have exchanges one after the other of pages. So you see in this code, I'm setting fetch size of 2, which means I'm getting 2 metals at a time. But still, you will see that I'm printing more than 2 rows here. So pagination with async iterators. Let me close the API and run again my client. Again, this is something I'm just doing because I'm lazy and I want to work in a interactive REPL. So this is the very same code you just saw in the slide. And you see I'm printing all metals. More than 2, right? That's because the drivers I just let the drivers handle all that. Another way, a very similar way, is to use the each row method and just pass the option auto page through. That's very much the same. I'll skip these, but it works again in an automatic way. The driver will take care of everything, and I will just magically see all rows that I need from the query. But sometimes I need to use manual paging. I need to have explicit control over pages. Think about a web application where there is a nice button, next results, in the interface. So it is the user that clicks and triggers the next page. So sometimes I need visibility over the actual page state for the next query. Indeed, that can be done with with basically, again, a combination of execute. So the first execute here, the first line, let rest set equal, will give me the first batch of results, but also potentially will contain a page state. Then until this page state is not null, so as long as it is not null, that signals that there are more rows to be obtained. I can explicitly read the previous page state and pass it as option, as you see here in this last long yellow line. I can pass the previous page state as an option to the next execute invocation, and there will be more rows to read. So this is how you explicitly look at the pages and handle them and control getting page after page of results. So this is manual pagination, and let's run this. This is exactly the same code that you saw in the slide. And there we go. So you see, I'm explicitly able to control page after page. Okay. In a similar spirit, I can also use the method next page that somehow automates handling of the page state. And that's very similar. Maybe I can show that to you. So you see how the page states look like. They are, as you can imagine, very long strings with which my client side is not required to understand. It just has to take them and give them back to basically the server. Okay, so there we go. You see, I am printing the first two lines, then I have a given page state that I'm giving back to the next page invocation, which happens here. I get another batch of 2 results, and so on and so forth. At some point, the page state is null, which means no more results. I remind you that I still set fetch size to 2 for demonstration purposes. Then again, if your row is small, you can also safely get all 5,000 or even more. If you start having very fat tables with a lot of fields, maybe very big fields and so on, you might want to make it smaller. So you might really have a use for fetch size 1, 2, 5, 10, whatever. Okay, so there are other ways to handle pagination. This is a nice way. So you can use the client.stream method, which provides an object to which you attach events. So you attach the events readable and end. And what is the advantage of this interface? It will lazily fetch items from the backend, from the database, in order to avoid, filling up your local buffer. That is a very valid option, especially when you are doing some kind of heavy or anyway long-lasting processing of the results, and you want to avoid, piling up results on your client side. So this again is easily demonstrated here, and again, it is just doing the same reading of all metals. You see that it's clearly stated what happens when. So please have a look at the code. All of these examples are basically adapted from the documentation on the website. So if you want to go there, there is much more to know. Obviously, this is just the first introduction, but should get you going already. Okay, so far I've been basically showing you how to run CQL commands the right way using the drivers. What you should know is that if you prefer to use models, actually the drivers offer also object mapper options, so you can work with models, and they are pretty clever, meaning that you see I can define a mapper in this way, so don't look too much at the details, but I can define this mapper in a way that it is able then to produce models for me, this element mapper, which is then able to support methods such as insert, get, or remove, and so on. And the arguments are just objects. So I'm able to, basically it's a model interface to the tables. And I say to the tables because the nice twist is that when you instantiate the mapper with more than one table, you see this new mapping mapper. I can give here more than one table to the argument. And if I do that, remember denormalization and duplication of data? Well, this mapper is automatically able to map insertion of a single object in the JavaScript code to make it to transform it into several insertions in as many tables. And that's very much a useful thing because in Cassandra, this is a solution that is very often used to support, for example, different queries. So just by looking at the column names, this piece of code is able to handle basically denormalization, in particular multiple insertions and readings. So it's a pretty clever thing. Okay, so my demonstration of the node part is over. This is obviously just a scratch in the surface, but I encourage you to have a look at the documentation. Let me just show again this alternative that is Stargate. Stargate IO is open source and it can be plugged on top of any Cassandra installation. It actually acts as a set of nodes which integrates with the existing cluster, and they are nodes that hold no data, but they can accept queries. So it's a very clever architecture, and they make it possible to just use HTTP request according to more than one different API paradigm. So yes, it's HTTP request, but actually there are SDKs for major languages to make it even more painless to use. And the nice thing is that it is just HTTP request in a sense. So, well, this has been illustrated better by Cedric, but you can use a document-like API, which, okay, here it is in Node, but behind the scenes, what it does is a series of requests. So you can also use curl if you want, Postman, whatever. So it's all requests. It can also support. It also supports a GraphQL interface, as you see here. But I'm not dwelling much on that. And I think I'm very much on time, and I come to my conclusion. That is, I remind you, if you want to run the code yourself, please have a look at the code sample. I will later paste this link into the YouTube chat. It's a self-service, so please have fun if you want. And yeah, here is where you can find AstraDB, which, by the way, embeds Stargate automatically. So Stargate is there already for you, so you can start playing with document API, whatever, just out of the box. Yeah, so you find one thing is that we as a DataStax developer advocates run very many workshops. Most of them are centered about usage of Cassandra or better AstraDB. And most of them, maybe all of them now, showcase the use of Stargate. So in this presentation, you saw much more about the drivers, but if you are interested on various facets of Stargate usage, please head to these links and have a look at our workshops, which all come in the form of self-service repositories with README as well. Then again, we have a few resources for developers. So Academy, if you want to get certified for Cassandra, but please connect with us on Discord, where the discussion goes on and on and on. We are happy to have friends there to discuss and help answer your questions, whatever. Well, that being said, the way ahead is long and interesting. Just go and create your nice Cassandra application. With that, I thank you. and see you next time. Thank you.
Imagine a being gifted with powers from the goddess of Cassandra, who grew those powers until she could multiply at will, move with limitless speed, and unmask hidden knowledge. With those powers, she was able to fully understand the connectedness of the world. What she saw was a world in need of understanding. From that day forward, she sought to bestow her powers on all who came into contact with her, empowering them to achieve wondrous feats.